I think it's working. All right, thanks. All right, good morning, folks. How are you all? Having the energy recovered from all the trip yesterday? You're okay? Still tired? But I think it was very relevant to what we discussed in the class before. So, how do you all think about the visit? Did you enjoy? Did you? Okay, wonderful. Okay, good. Thanks. So, I think we started with drought the other day, but again it's going to be in-depth analysis, or at least looking at some of the drivers of drought and talking about specific drought indices that you can all use in your research if you are interested. I am going to dump bunch of papers. There are about 20 or so papers I have on drought. So you can download. At the end of today, I will post all of those papers. So your assignment is to quickly read at least the papers that are relevant, apparently relevant to your interest, that picks your interest, and then maybe you can discuss with me about the details if you don't fully understand that paper in the next few days. So that way, at least you will be little more familiar than just talking about the theory here, right? Because we don't have a lab session for doing drought modeling, unlike HECRAS, HHMS for flood modeling. So that is where I think your interest, drought modeling is not difficult. It's an offshoot or an extension of hydrological analysis, hydrological modeling analysis. So if we are planning to have SWOT simulation exercise on Monday. If that happens, the output that we will have from SWOT model is used in many of my own papers, or some of the papers that my scholars and postdocs have done. So you should be able to really go back to your place and conduct drought modeling analysis on your own, really with a very short learning time. That's how I feel. Okay. Coming back to today's lecture, first hour I am going to take Dr. Venkat Reddy sir will come after that, and he will continue for 1 hour, and then I will come back again to finish this lecture. I have some videos to show you in the meantime that I am actually seeing. It's all publicly available domain software or videos. We will, at least for the sake of creating some awareness in different continents, we will have to kind of see how they think about drought, which is more or less the same thinking that what we will have in the next 1 hour session that we will have. Is the light too bright for us to see the screen? Should we turn off or dim it a bit? That side, that side. I think that's all. No. So you remember I showed you the pot with a plant last time, and we talked about putting water in it and it was draining, right? So you can see the available water holding capacity between field capacity and wilting point is the one that supports the life of this plant, right? If it falls below this wilting point, plants will start wilting. That's exactly the meaning of it. And this is the place, the field capacity, when it reaches up to this point, anything that you apply on top of this will start draining as excess percolation. So the water that's available freely in this root zone depth, this root zone depth that I am talking about, between field capacity and wilting point, for every soil, whether it is silt, sand, soil or clay, you have numbers, tables available to say about field capacity and what is the wilting point. So just it's a number that will tell what is the available moisture for the given type. If that available moisture is gone, plants will show up as suffering, and that's the drought indication. And we are modeling that. Basically, we are quantifying drought using some of these variables that I mentioned before, which is basically all the basic hydrology variables. precipitation, temperature, ET will come out of the model. Stream flow will be simulated by the model. Soil moisture will also be simulated, and groundwater. So these are the two variables that we primarily use in hydrology models, and the rest are um, parameterized that you saw from your last exercise on HMS, right? So HMS also comes up with some quantification on stream flow, and then change in soil moisture for event based analysis. It's kind of considered minimal, but when it comes to drought, change in soil moisture storage is the biggest one for considering soil moisture based drought indices. Okay, soil moisture based drought indices are much more reliable to predict drought uh, than temperature only or any other single independent variable. We will talk about that. So there are basically the concept of floods versus drought, if you look at, is the negative anomaly from the average soil moisture condition or precipitation condition causes your drought, but the opposite is the case. When you have excess in moisture, then the runoff starts. Basic definition of flood versus drought, that in terms of anomaly. I show this map. It's not directly relevant to our interest here. This is the US map for precipitation. This is for drought map that we simulated. So this is based on observations. This is based on the models. Okay. So the thing what you are seeing here is 1901 to 2018, when they calculated based on precipitation only, what is the heaviest 1% event, rainfall extremes. Basically they are ranking all these places. Northeast here, Washington DC is somewhere here, my place is close to that place. So we are talking about above normal precipitation, higher in number. Basically, anywhere from 20 to 40% increase in precipitation in blue areas, and less precipitation in other areas overall. And of course, in the future we are looking at floods more, and also you have droughts in southwest areas and southern area. This is Texas, this is California, right? So you are talking about drier conditions. So most of the country is expected to get more rain and more floods, like India. I think in climate change conditions we are talking about more rainfall for India, at least 10 to 15%, right? So that is actually is the historic number. This is the future projections. But then the same country is also subjected to extreme drought. This is based on US drought monitor D0 to D5. Exceptional drought is this one, and moderate or abnormally dry condition is D0. This is US drought monitor. I will show you in another slide, but what I am talking about is some of the drought metrics that we calculated, which you will be knowing soon in the next few slides. We are able to predict drought for the whole country using SWOT, using WIC model. There are two different models that we used to predict drought on a countrywide scale here. One is a semi-distributed model, that is SWOT. This is a gridded model, WIC model, which is a resolution of I think we ran it for 0.25 degree. So what I am trying to say is the drought that we predicted and compared with drought monitor are more or less showing the signs of drought in the northern part, in the central part. And also you see here in the scenarios like here, the same place where we have extreme flood events are also subjected to extreme drought. So that is the future, and that's what we are supposed to be ready with. And I think I have a newspaper clipping, and somewhere I will try to show in the next hour. When I was leaving last week, it was heavy rainfall in the airport that I was trying to come out of. The same northeastern portion here was completely closed for heavy rainfall events, starting from Boston to New York to Washington DC. All the places were shut down. That was the reason for my delay. But the next day, the same airports were also closed again because of heat waves. You see the swings that we are talking about in climate change scenario. 7,000 airports they closed maybe next to next day, it affected the air traffic control, completely. Um, so we are looking at these kinds of things. So don't be surprised that when I say floods in one place, it doesn't mean it's going to be insulated from drought. And we are talking about India in the same way. Western Ghats getting heavy rainfall one year, inducing landslides, but the same Western Ghats will also be subjected to flash droughts, to severe droughts um, next year, right next year, if monsoon fails. Monsoon can fail based on yesterday's discussion, ocean heat content, that what we are talking about, it's changing the whole dynamics that we saw from previous discussions also. So oceans play a big role, and now if you look at the country-wide average number of PDSI, I'll talk a little more about what is PDSI later on. For the available period of record, about 130 years, you see here the swings that basically we are talking about, going up and down, wet condition, dry condition. So every once in few years you have deep drying conditions and drought, exceptional droughts, -4 or 5, but you also have wetter periods. So this is a challenge. That's what we are trying to really address through this class, right? So we want to, this is a time series. This kind of data is available for the whole globe. You can easily download, check, just, I mean, don't think of just as a research question itself, but just to inform yourself what's happening in India. If you want to really understand, there are, I think this is not the same source that you will download, but on a global scale, from NCAR or some other source, it should be available. Google search should tell you 2-degree resolution is available for PDSI on a global scale. You can download few of those grids for India or for your own region and try to just plot whether it's Marathwada region or maybe central India or eastern India, North India, just to understand just quickly about what is happening. The other fancy way of looking at is, of course, how many acres of land are impacted by um, each of these drought classification. So there are 3 important ones that I mentioned before, right? Severity, area, and duration are 3 different metrics, plus onset and the termination time of the drought are going to be really important for us to understand. So this shows different types of droughts, the severity aspect of it, over an area, for how long. So that is evident from here. So all those 3 metrics that I am talking about are shown in this nice graph. You could do the same thing again, replicate this approach for a study area that actually should inform you to even set your research questions before even you start proposing your proposal, topic, just to say why you want to study drought, because this is the motivation. This many areas of acres of land are impacted by drought. So this often we see, this is the kind of setting that we are having in this land. So how do I predict it, or how do I project it into the future, or how do I forecast into the future, right? That's a kind of thing. So basic thing for drought analysis, you need long-term precipitation observations, right? Definitely. And then long-term soil moisture observation. But we don't have soil moisture widely available for many places, including the US. But we have, they call SCN networks, conducted or maintained by US Department of Agriculture. They have some network, soil moisture network, that's what they call it, pretty dense. If you want to even explore science questions using that, that's publicly available. You can download and use them. Although I don't have the website in my slides, but one of my papers may have, some of my papers might have, so you can look at that. And then the list of drought indices I'm going to first list here: standardized precipitation index, Palmer drought, modified Palmer drought, self-calibrating PDSI, hydrological drought index, Palmer Z index, standardized precipitation again for future outlooks, and then SMDI, soil moisture based drought index, which is also connected to soil water supply index and standardized soil moisture index, evapotranspiration drought index, standardized base flow index for groundwater, multivariate standardized drought MSDI, and all of these indices are kind of relevant in one way or the other in some of the many of the papers that I am going to provide to you. But I kind of started tilting towards soil moisture based drought index. Most of my papers will talk about that, but the other papers are really, people have already done. Standardized precipitation index is basically one of the most popular ones from, you know, many years ago. I think people started using it, and of course it's a simple approach to calculate. It's a normal distribution of precipitation. I'm actually going to skip that slide to just show you this equation. This is like Gaussian distribution, right? X minus mu over standard deviation. So precipitation data is typically fit as gamma distribution, but then transformed into standard normal distribution. So that's what this SPI index does. Precipitation minus mean precipitation over standard deviation of precipitation. If you calculate, it gives you an idea. You can do multi drought indices comparison starting with SPI, okay, but it has been very well established in many parts of the world. So you will be reinventing the wheel if you are just using SPI. So that's, and again, SPI does not tell you all the story about drought. Okay, so it's giving you an idea about what can happen based on precipitation only. It does not consider soil moisture. It does not consider how plants respond or groundwater response or stream response, but that's okay. It can give you a rough idea. But Palmer drought severity index is little bit advanced. If you look at this equation, it's basically a previous time step PDSI determines in addition to your anomaly index, that what we have here. This anomaly index Z is basically P minus P cap over alpha. P cap is called this climate adapted or affected, climate affected effective precipitation or existing condition, CAFEC they call it, or CAP. So basically this number is derived based on potential ET, recharge, runoff, so loss. You are able to get these numbers from any hydrology model. If you have data, that's good. If not, simulation model can actually give you this number. Calculate Z, put that in here, come up with the PDSI. This is a time series. For the US case, it's already calculated for every small box or grid that what we have here are called climate divisions. Here, equivalent of a district size, I would say, equivalent of a district size. For every county or climate division, they can plot like this. Same way you can do that for 500 plus 600 plus districts that we have in the country. If you calculate, maybe it's available, check it out. If it's available, just extract and plot them both spatially and temporally and look at the trend. Palmer drought severity index is a widely used index. Yeah. Once. Which one are you talking about? Yeah, PCAP I call it. This is derived from the climate appropriate precipitation. Basically, water balance number, that is your P or sorry potential ET. I have this equation, one second. I think I may have that equation in another slide also. Yeah, here. So P cap is calculated as summation of PET, or that is recharge, runoff, and loss. Loss is considered like anything that you cannot account for. So if you can use the same thing, the only thing of course is that you can do that PDSI on a daily time step if you want, but if you do it on a monthly time step, it becomes your PHDI. Or if you modify this PCAP with some additional coefficients that I show, that becomes your modified Palmer drought severity index. But it's basically nothing but climatologically appropriate for existing conditions. CAFEC they call that, CAFEC precipitation, that is called PCAP. uh, actual evapotranspiration becomes precipitation. No, no, actually it is not P, because P is 100%. Actually it is about 60 or 70% of potential or precipitation. It's reduced already. Actually it is having some control, push and pull from the soils and vegetation, environment and everything. So you cannot use actual ET. Yeah, and also PET is the maximum number in terms of evapotranspiration. PET is the upper bound, so that's what we are using here as, climate appropriated condition. This is, so again, you would not need to calculate. There are lots and lots of algorithms that are already developed for you to look at. If you just find out Z index algorithms are available, but you need to know what's behind that. So that's why I'm trying to break it down like this. Those who want to start from scratch, take these equations and try to really quantify each one of them and try to really understand what's happening behind these indices. I mean, these are, if you consider them, these are like binary, right? 0 or 1 kind of numbers, but you need to know how these numbers come from, how do you calculate, right? So that's why I'm putting these equations here. Modified Palmer drought severity index, there is some sophistication going on in defining this CAFEC. Okay, so you look at these algorithms later, but all I'm trying to say is this CAFEC is of course reduced from precipitation, and look at all the other changes that are driven in these Z calculations. We substitute with modified algorithm that takes into account some of these advanced computation. The main difference is, of course, if you look at the potential evapotranspiration, potential recharge, runoff, and PL is the potential soil moisture loss that we have here in this case, and that is probably not mentioned explicitly in Palmer drought severity index CAFEC, because they consider that as loss, very generally speaking. But the rest of the formulations are the same, but that you apply here, the previous time step plus the anomaly, come up with modified drought severity index, which we use in our calculations. We need soil moisture for this. Once you get that from the model, modified Palmer drought severity index, you can easily calculate. When I am talking about drought index like that, I will also show you the website where you can even download that program. Oh, I thought I had it here. Yeah, see here, I just, this is self-calibrated modified Palmer drought severity index or Palmer drought severity index. So they give you, go through this code here, it might give you some idea. For all the equations that I am talking about is here, but they have given the sample code here. It's a MATLAB code. How many of you are familiar with MATLAB? Okay, so I mean, that's a starting point for you to really use these kinds of existing codes to understand one index like that, right? But you can also modify based on your interest, PHDI or MPDSI or other things. Self-calibration means you don't really do calibration by yourself. It's kind of an automated way of doing it. But again, that is a slight modification to the existing PDSI. Modified Palmer drought severity index is also we use in our analysis. Z index I talked about, but again, these are considering some of the factors that are useful, but there is some randomness associated with any of these meteorological or hydrological variables, right? So they actually need to be accommodated. It's not one variable that actually helps you understand drought extent. So we want to use multivariate standardized drought index, in this case MSDI, with multiple hydroclimatic variables. So many times we end up using a joint distribution between two variables like precipitation, soil moisture, precipitation, runoff, or precipitation and ET. All kinds of combinations we can have for a joint distribution. You come up with that distribution, which is much more weighted condition for predicting drought than the previous set of numbers that I talked about, like PDSI, SPI, MPDSI, or Z index. All four of them does not take into account some of these randomness that we have in hydroclimatic variables, but you can include. in this approach. So we ended up using MSDI in many of my papers that you will see. So MSDI is also useful. I'm going to actually quickly talk about flash drought, because there is some interest I see here in this class. For some of you might be using them, so I just thought I will extract some material from our paper, published paper. I show here, this is also available. Just try to read them if you can, and I will also have this PDF available to you, as I said before. Mainly the small or simple difference between regular drought to flash drought is it's a sudden onset that you don't even know, and it rapidly intensifies, primarily because not just your deficit in precipitation, but also abnormal heat waves, low humidity and strong winds. Those three things happen. It can happen, right? We saw dust storm yesterday coming from Arabian Peninsula region entering, or maybe from Thar to some other place within India. You might really have those kinds of quickly aggravating conditions in central India from somewhere from the west, right? Or north to south. Those kinds of conditions can quickly evolve into a flash drought condition. We saw flash floods because of urbanized conditions. We say that sheet flow happens, overland flow happens very quickly. I think in fact I have those slides here, right? So that graphic, that's flash drought or flash flood, right? We are talking about advancing from undisturbed watershed to a disturbed watershed like urban watersheds, where the peak flow comes quickly, and it is the also part of the flash floods. Here it's flash droughts, primarily increased evaporative demand and soil moisture depletion that happens. Desiccation, that's called desiccation. It can happen from many ways, right? Zonal flow, meaning horizontal flow coming from the ocean or from the deserts, right? That is one thing. The other thing is jet stream. You remember I talked about high level jet streams, 10, 15, 20 kilometer height. Those are dry air. Even though ground condition can be cold in winter, in December, let's say in Delhi, it doesn't mean the whole atmosphere is cold. This constant flow of air mass, jet stream, that kind of comes down to the north from Himalayas, still have hot air above. If it descends onto the ground, it can also quickly heat up the surface and desiccate the land, dry up the land basically. It happened before in many places. That causes drought, very intense, severe drought. So that can also be the case. Now what we did was we calculated soil moisture index again, soil moisture based drought index, but we put it in the context of flash droughts with pentats. Pentats mean 5-day average. You look at the paper, you'll understand how the analysis is done. But we use two different models again, SWAT and WIC, because one model alone is not sufficient. Why do I say that? I kind of copied this climate modelers approach, frankly speaking. Look at climate change predictions. You are talking about RCPs, 4.5, 8.5, in the middle also you have 2.5, 6 point something, right? Same way with your SSP, so many scenarios they come up with. Why? They want to predict the uncertainties, they want to bracket the uncertainties, right? In the same way, if you just rely on one hydrology model, that may not be sufficient to bracket your uncertainty, because we don't capture all of the processes. I talked about just precipitation going through vegetation, through fall, through flow, stem flow, and then canopy interception, canopy storage, and then you also talk about depression storage before it starts flowing. Are we modeling all of them? Just to recall your memory on the discussion we had the other day, all of these terminologies are lumped into something in the equations. We don't even represent them correctly in any model. But if you consider different models, you will at least see one or the other model will kind of have this broad range of uncertainties accommodated. That's the idea. So that's why we use two different models here. Coming back to the prediction here, this is done for the Mekong region. I may have additional slides here. I thought I had it, but let's see. I focused on the Mekong River basin for this. We looked at the dry season there is December, Jan, February, and pre-monsoon, that is March, April, May. They also start getting rainfall in May, similar to here in the Mekong basin, which includes 4 countries primarily: Thailand, Laos, Cambodia, and Vietnam. That's in Southeast Asia. And primarily in the future we are going to have more flash droughts. That's the prediction that what we are saying. It's consistent with many other studies that what people have come up with. The last one I wanted to talk about is this anthropogenic drought or socio-economic drought. This is another important terminology people are coming up with, because you don't want to just consider physical variables only to quantify drought. What are the physical variables we talked about so far? All of the above, right? Like soil moisture, runoff, precipitation, temperature, many things, right? Like that, those are physically measured variables. But now anthropogenic conditions consider humans in it, right? We are talking about population growth, industrialization, agricultural demand, greenhouse gas emissions, land use change, all of them are integrated. So I show you this paper. This is kind of a seminal paper on the topic, which might be of use. Just, I don't think I downloaded this for you. If you need, I can, let me know, but I think you can also find out. This is a ERL paper, I think, Environmental Research Letters. The idea here is, we talked about modified water cycle on day 1, right? This is natural. Now this is all humanized, modified watershed with lot of houses, lot of agricultural lands. So the demand increases and the outflow is decreasing here. So we consume more water in the upstream portion itself, right? So that's the setting for socio-economic drought or anthropogenic drought. And all the other metrics, I mean, you can include, basically when you want to calculate anthropogenic drought, what do? Basically you will have to consider water supply metrics. How much is the inflow? What is the outflow? In all the other ones, we are talking only about soil moisture and basic things, like for both all types of variables, I mean droughts. We talked about the other day meteorological drought, agricultural drought, hydrological drought. All of them just need physical variables. In addition to that, of course, here when we talk about anthropogenic or socio-economic drought, we want to understand what is the consumption, how much is available, those kinds of things will come into play. In any case, as I said before, this is our one of the heavily used model. This one I have been using it for quite some time, but lately I am not. So if you ask me the details about the model, I might be I might need to refresh my memory on this. It's a very detailed model. HRUs that we saw the other day for I'm sorry, I think I missed the connection here, but nevertheless I just want to explain this. If you see here, they divide multi-layered columns, right? Like layer 2, 3, 1 and canopy layer, and then they partition the incoming precipitation into rainfall, runoff, discharge, base flow. Within the grid also they can divide based on the distribution of vegetation. That's the spatial variability that we try to accommodate, and the infiltration is based on this exponential curve or non-linear curve that we have. That's the beauty of this model, to identify how much is the variability that we have with respect to soil moisture based on this infiltration rate. Sophisticated approach is that one, but here also we have HRUs that you define at 2 hectares level, right? Smallest scale that you can have here is very high resolution. You can of course then use curve number to do the runoff. You have all the other methods to calculate losses, same as your HMS the other day you did. So these two models are common. We use all this. Now I'm going to be talking a little bit about the papers that we had published. I will show you a few examples, basically to say that it is your need that you need to identify whether you want to have seasonal forecasting to be done for drought analysis or long-term projections, or you want to look at flash droughts, right? All three are different. And then if you want to look at anthropogenic drought, you need to look at annual, includes reservoir storage, inflow to the reservoir, outflow, demand calculations, and then looking at all the other things. So that is more of an annual scale event that we are talking about. So different scales, that's what I'm trying to get. So we used CFS model or forecast, which is available for the US up to 9 months forecast that we have, temperature, precipitation. We took all of them, we used in our model setup to predict soil moisture. Although we were partially successful, I'll say why we are partially successful. We were able to showcase the need for using this data. That is what the objective of this paper. We tried to really improve that based on what variable we should use to predict seasonally up to 3 months time, and when it falls apart, right? How it falls apart is this: basically we are talking about temperature more or less identical, but precipitation is not. So that gives a problem. That is the whole idea here. This is precipitation that does not agree. As you can see here, temperature is really more or less good. So the forecast period. So using temperature and precipitation to predict soil moisture based drought index has some uncertainties. That's what we are trying to prove here. Particularly that uncertainty comes from precipitation more than temperature. So temperature is reliable, precipitation is not reliable for forecasting all the way up to 9 months of time. But it's okay, what we say was it's okay up to 3 months or so, if I remember correct. So you can read that paper. So it's kind of applicable for you to apply this kind of approach. You may want to use GFS forecast, which is global forecast system, right? So that's available. Maybe resolution may not be the same. There may be newer products. This is little bit of a dated paper, but you can find similar data sets and experience or experiment different kind of strategy here to apply. The other paper, I think I mentioned this on my day one talking about climate change. This is from Deepak Bisht, who is a scientist now at NIH. He'll be very happy to help you if you need anything. You need to just let me know, because he's been very active in supporting hydrological work, very active scientist. What I'm trying to show here is his work as a PhD student at IIT Kharagpur. I was also part of it as a co-author on this, so I can explain briefly. As you saw on day one, when I was showing here, this is your the duration, this is the occurrence, right? We have basically quantified drought, coming up with future scenarios of RCPs and extensive, future scenarios up to 2100 or 2099, right? So you can see central India is going to be baked, it's going to be dried for sure, more or less, because I think there is some connection to what may happen to precipitation, right? That's a vague interpretation we can have, but it does not include monsoonal changes. Think about it. Yesterday you went to Inquois. We talked about how the oceans are changing, how ocean heat content is going to influence monsoon precipitation, which we also saw the weaker circulation, or how Arabian Sea heating sea surface temperature can influence modification to your southwest monsoon initiation, right? They said it came few days before this time, earlier than the period, actual time, which is June 1st, right? It may happen in the future, it may get delayed. We don't know. That is not included in this analysis. That is something to consider for the people who are on the west coast, including Marathwada region, where drought is very common, right? So we are talking about this region. We are seeing drought in almost all the maps here, right? So this is about 5-6 years old. If you want to even replicate exactly this work with newer data, that might even add value. Using, this is I think using WIC model, I guess. You can check that. I forget, but I think it's a model prediction, based drought conditions, that what we are showing here. Multivariate drought index is a statistically derived index that I talked about before, but again I'm showing this. They call it, there are umpteen number of drought indices, right? That's the purpose for me to show. They call joint drought index, basically using precipitation stream flow in this case. That's what it's called, joint distribution, right? We used MSDI with stream flow or soil moisture with precipitation, but there is also an advanced method called cupola based distribution. It's another fancy approach. One of my students long back, he did this work using cupola approach, which was a good paper. Basically all we are trying to do here is you have marginal distributions of multivariables, bring it in the cupola context, develop joint distribution, whichever ones that you think are relevant. I am just giving you bird's eye view of this approach, but the details are here in this paper. We can, if you want to apply cupola approach, I can talk to Madhusanka, who can make some codes available to you, and this is again dated, but we did this for the Mekong basin, right? Mekong is also subjected to drought. So if you recall my work that I was showing so far, some flash flood events to annual scale drought events to climate projections using physically based models as well as stochastic approaches and joint distributions that we have done. So anything that you can imagine is done only in the physical sense. It's not including drought coming or impacted from socioeconomic conditions. So that's another opening for you guys to think about, using the similar approach but extending to socioeconomic conditions. That might actually be useful. We did though one additional stretch that might be relevant to Indian context. The same thing. I'll talk about this drought paper, which came out in scientific reports, where we looked at the lower Mekong region. So this is the Mekong basin. I think I may have shown before, but again, this is this long skinny, it's same length as Ganges. If you think of Ganges, about 4,000 plus kilometer length, it's about the same. It flows through 6 countries, China, Myanmar little bit, but then all the 4 remaining countries, Thailand, Laos, Cambodia and Vietnam is here. This is the place it drains. It's South China Sea here. We actually clipped the southern portion only, that is lower Mekong. We call this as a lower Mekong region. There are 70 provinces that we have here, right? We also use SMAP based soil moisture. I'll talk about remote sensing based products that we can use for drought analysis that might be of use for India also. So traditional calculation of drought indices are okay, but this is a heavily irrigated area. Our farmers are affected by not knowing what's going to happen to their agricultural yield. So we flipped the question, what is the difference between drought year versus non-drought year when it comes to crop yield? That is the first basic question we tried to ask through our first question. And then we came up with some numbers of yield. I don't show all of them, it's in the paper that you can check. You need to have crop yield data for this analysis. You can get, I think in India, we have that data available, we can see that. And then we came up with provincial scale drought maps. This is ditto from the all previous work that I showed you. Soil moisture based analysis that you can do, ET based analysis, well, anything that you feel comfortable to come up with, could be even SPI based, simple ones, or Z index or anything like that, right? PHDI, PDSI. But the drought map is showing the yield change between drought and non-drought years, okay, in tons per hectare. Okay, the next question, sorry, paddy, mostly rice crops, yeah, they are irrigated, heavily irrigated, yeah. So we then thought, okay, now you are seeing the yield difference because of the drought. You don't see green areas much, right? I mean, if you see here, more or less it's in this range, some reduction in the crop yield. People don't see that way, right? Yield drought versus non-drought year, generally they say okay, it is affected, but we quantified that over a number of years basically, and this is a what, 25 plus 15, 40 years of data. That's rich for us to understand what's happening based on crop yield alone. And we were able to bracket multiple drought events between those 40 years time. And we also looked at the future, but then we asked, another interesting question. That's how it turned out to be an interesting paper in scientific reports. What was that question? The question was, how much more lands that you need to irrigate to compensate for this loss? It's a very simple question, right? Now that actually helps the policy makers to really make some decisions about where to invest money for infrastructure, irrigation infrastructure, for example. So that's a very a simple approach that we did, and we came up with, I don't have that map here, but that's in the paper that you can refer. We said these are the provinces in this country that you should have more irrigation infrastructure. These are the provinces. This is still coarse, it's not really going at the field scale, but somewhere you have to start at the core scale first and then go down deeper later when you find out that that is the province that you want to improve irrigation. So this comes under food security. Drought relates directly to food security issues, water security issues, right? For India, 70% of farmers or communities, population that rely on agriculture, if you do something good about protecting the crop yield under drought conditions, that's a phenomenal contribution that you can have for this country, right? That's obvious, because we are going to have drought many times. Even though floods come and go, drought for the remaining 9 months a year, you don't have enough water. You don't have water for drinking, you don't have water for agriculture, hydropower, navigation, fish, environmental flow, whatnot, all kinds of demands that you have, but primarily agriculture. So this question you want to ask through some of these fancy research questions and using the tools that you can answer those questions. Okay. Again, I think I mentioned this US drought monitor before, but I'll show you. I think I may have talked this before, about this before. See here, I think Southwest is always dry, right? So they come up with these weekly maps. I may have mentioned this another time also, right? So D0 is abnormally dry, D1, D2, D3, D4, which is exceptionally dry. This is not just based on soil moisture only or temperature or precipitation only, right? They also do phone calls to connect with people at these places and then get some feedback on what is their water supply condition, something like that. So they come up with this map every week of drought maps. We use this as ground truth. Many of the modelers use USDM as the ground truth. There is no other way other than that, right? Unlike, for example, in stream flow modeling, you have observed data from gauge station, you can validate that and say whether or not it's good. What is the validation data for drought? Nothing. Right? There is no obvious thing other than looking at crop yield indirectly. Like yesterday, scientist from INCOIS, he was talking about how, kind of inferentially they derive the information, where to go for fishing based on salinity, based on, chlorophyll content, right? It's an indirect inference, and then they catch the fish excessively in one place based on those currents and how the warm water that is coming close to the coast, and they are all going there or jumping from there or whatnot. So the same thing happens in drought cases. You don't have really drought variable as such. You have to do some indirect measurements or indirect validation, which is the one. Here in this case, you can use, if you are using PHDI, for example, let's say hydrological drought, you can say based on stream flow conditions. Again, that's an indirect reference only for drought. People are suffering, yield is less, economic activity is going down, people are bringing water from in the trucks. Trains brought truckloads of water for many cities. Those are kind of quantification to show the severity. Maybe you will have the maps. I think it's produced by some institutions here in India that you can refer to. I think IIT Gandhinagar, that you may be able to use the data for validation. I did not talk about ETDI, evapotranspiration deficit index. I am just showing this here for your material for reading later on when you get back. ETDI is another good one, but as you know, ET is the most complex variable to quantify, to measure, even to model, right, because of the uncertainty that we have with plant canopy to forest to urban areas and all kinds of issues. But ETDI I have not used extensively, or not even once, I guess, but it's a good one to use. I like to use it, but no interest or no data to do that. Okay. So, PDSI, some basic information is available that I just wanted to show you. You can refer to this material later on. There are some shortcomings for each indices, but I just list for a few. It's self-explanatory, so you can read by yourself and understand why we use certain indices. So, I am just, in the interest of time, I am going to stop with all these discussions here. Multivariate drought index, I think I talked about all this before. Uh, the important point that you want to know, I think I talked to some of you yesterday about use of indices, certain indices, right, for agroclimatic zones of India, that we said there are 27 variables, how are 27 indices that are available, how do we pick, what do we pick, and those kinds of discussions were happening. So, what I wanted to say, that is not just confined to that analysis, that same confusion happens even for drought analysis, because I showed you what, a dozen or more indices related to drought. So, you cannot do all of these drought calculations for all the sites every time. So, you need to pick what is the most relevant, depending on your need, depending on your question that you are answering. So, you do not have to do all of them. So, the main thing is, of course, I wanted to, if you are talking about reservoir operations, the inflows and outflows are important, demand calculations are more important, and see how that is changing over time with respect to climate change, land use, land cover change would be important, population increase would be important. So, there is a, when you are talking about these indices, they are not the same, right, they are going to have some lags. Groundwater index, when I am talking about, you will not really see change in groundwater right away. There is a lag of recharge, even a few months to a year or two. So, you have to identify if your watershed is groundwater dominated, and if you really want to understand the impact of drought on those resources, groundwater resources, then use base flow index, right, some of those drought index that are related to groundwater. But if your watershed is prone for flash droughts, use SPI, use some of the instantaneous ones. But if your watershed has got fluctuations on an annual cycle with precipitation, maybe PHDI with stream flow conditions that you can have some idea about. So, this particular slide talks about how do you select for western US, in this case, for surface water supply index. If they just use only precipitation or snow, it may be not sufficient, because the reservoirs receive snow melt induced runoff and they accumulate in addition to precipitation. So, they want to consider western snowpack. I think I mentioned this to you. They predict by April 1st what will be the amount of water that they will have from this pack of snow that is accumulated over the winter, and that is included in the calculations of surface water supply index when they consider all the reservoirs receiving snow melt runoff. So, you have to kind of think critically about what would be relevant. If it is an agricultural watershed, crops that are more important, anything related to crop, anything related to biomass, that is more important for you. If it is really industrialized place or commercial place, populated areas, you are talking about demand calculations to be considered in that case, right. So, what are those metrics that you would use? So, paying attention to that is very important. The next part I wanted to say is, we talk about climate models, right, like 10 models, 15 models, 20 models. I want you to stop a second and think about have you ever thought about choosing a few models from those group of models, or do you think you can run the whole set of scenarios based on all all combinations? What's your take generally? What do you normally do? How do you select? Okay, that based on ground truth, based on how climate models have predicted the past conditions, right? So that's still there, but what else you do? So you see a lot of models are agreeing. Still, do you want to use all of them? What do you mean by that? Okay. Well, yeah, that is getting too much into depth before even choosing what type of models you will use. Right? I mean, you will know it only when you run the model and get the output from combined model of hydrology, climate models and all that. Mostly going with literature, that's another possibility. What else? What other answers I can get from you? Okay. Yeah, you are also touching that point, but I wanted to have little more clarity. What I normally did, I'll show you, then you agree or disagree with that. I plot all of the models first. Temperature change on y-axis, temperature change or precipitation change on the x-axis, right? I have all kinds of models here listed. This is for previous generation climate models, right? I choose, I want to make sure that I capture the brackets or the range that I am talking about, right? I always mention dry, that is one of the driest model that we can think of, because you have high temperature. I'm sorry, this one, the high, I mean, the minimum precipitation, and there is some temperature change that you have. Lowest precipitation, I call this as dry model, right? And I call that as dry and hot model. Temperature is relatively high. It's also kind of middle range of your precipitation here. Not zero, but not at the higher level. So I call dry and hot. I call wet and hot here because you have highest precipitation but hot model. And then I also call wet and cool model. This is wet model because of increased precipitation, relatively cool compared to this model. So when I am looking at all four models here, all four corners here, dry and hot, wet and cold, you know, um, uh, dry and hot model. So likewise wet and cool model. So all combinations that I am drawing here. I don't want to leave this model out for sure in my analysis. So when I put this graph like this, you see the randomness here. You don't have any models agreeing, right? Every model is behaving differently. You want to do this kind of analysis for your study area. I mean, going in depth with all the other attributes that you are telling to distinguish, certainly possible, but just looking at climate model data, just to plot them and see uh, whether or not you want to consider some of these outliers or models that really goes beyond for coming up with a better bracketing of uncertainties. Okay, so I think we are up to our time, but the last part I want to say here is calculating all these drought indices using the data available from remote sensing platforms, because many times you may be able to directly get them instead of simulating through models. Hydrology model, you can bifurcate or deviate from hydrology model implementation by using these remote sensing products, right? Some of these are out of date. Maybe we are here at NIT Warangal remote sensing group, volunteers are here, and Dr. Reddy is also here, Venkat Reddy sir, he can tell you more about remote sensing products which you have already discussed anyway, data sources in the first day. You can even go in depth now, specifically if you design your experiment, research questions, what are the remote sensing products that you want to use? That you can ask from the available folks here in the next few days, but I am just initiating the discussion here through the set of slides before we close this for a break. Precipitation is one of the commonly measured ones. GPM is people are using right now. Persian, TRMM, TRIM data, TMPA are used. Some of these data, for example, I'm showing GPM here from this NASA site that you can download. iMerge data sets available for cloud-based analysis. Is again, some of these products are easily accessible. The other one, evapotranspiration, that I mentioned to you before, I did not use it so far in my drought calculations because of complexity with respect to coming up with simulations. But nowadays, remote sensing based ET models are available, surface energy balance models that can come up with ET based on MODIS ET or Landsat ET. You have high resolution ET maps that you can directly use to calculate ET to use for your analysis. Soil moisture is another interesting one. We are talking about microwave data of soil moisture that's available. ANSERY, SMAP is another product that's used currently for drought analysis, crop yield forecasting, land atmospheric interaction studies. And then European Space Agency's Climate Change Initiative Soil Moisture, ESA, CCISM they call it, for almost for 22 plus 23 what, 45 years of the records that you have. Standard data sets. It may not be of high resolution that you want to implement for your study area, but for quick and dirty analysis, if you want to just start this kind of analysis and then extend into physically based modeling, compare remote sensing based drought analysis versus physically based model derived drought indices with even including machine learning based, then it becomes a very attractive research topic for you all. But research topics, we will talk about that later on the last day. The last variable that I want to say is groundwater change, which is actually measured nicely by GRACE. We have couple of papers that I put out in my drive. You can see the change in groundwater flux, of course, is considering soil moisture primarily and snow water equivalent. In this case, we don't use snow water equivalent. So total water storage, which is basically from surface to all the way up to your aquifer, saturated zone, roughly speaking. The amount of moisture that changes there tilts the gravity or changes the gravity force, that is captured by the satellite GRACE, and we have converted this into groundwater, for groundwater analysis, groundwater based drought analysis. We have used this for using in the machine learning framework multi-layer perceptrons, and came up with this GRACE data is available only for 25 years, or sorry, 2002 up to 2022 or something. We are extending all the way up to 1960 for 4 basins in the south, basically including Krishna, Godavari, Kaveri and Pennar. We have done some work that goes all the way back to 1960. That data is available, GRACE data that I am talking about, which can be used for drought analysis and looking at how drought can be predicted in the machine learning framework. I think we are pretty much done with my part of the presentation, but are we breaking now, or are we going to have the coffee break before? If so, I want to actually stop the recording if possible, then, because we can just show some videos here and then discuss a little bit. It doesn't need to be recorded. Whatever. Is it coming? 5 minutes I can show this video. It's a very nice one which kind of summarizes everything that I talked about in the context of Australia. But do you want to play the video, or that? I mean, it's not needed, right? Because it's kind of a casual discussion that we are having. We can have that, and I also make 2 other videos available to you later on. But it's basically an interesting one for Australia. 3-minute video, it's not too long. Don't.
Good morning. I hope all you enjoyed yesterday's program. So any logistics, just I think you bear with us. Sometimes since it is a program, so it's very difficult some logistics, but otherwise everything is fine, I think. Yeah. So we will go continue with the today's session. Morning I think Sari is explained about a few aspects of drought and how to model. Now we will go with one more interesting topic actually. It's related to the how the extremes which we can see, what may be the some reasons, can we able to understand those reasons, can we able to some quantification or modeling, that's what we can see here. I think yesterday's one of the important lecture which is happened in the afternoon, I think you followed, that is explaining about the different extremes only, is explaining about cyclones and other dust storms, other things. Are you followed the thing? So he explained about some of those things are happening and they are having a lot of issues, and of course some are happening but they will have other positive effects also. But some of the things which we know, we don't know that what are the reasons. So we think that our conventional climate change, all things, but there are so many other things are there involved. Okay, so where there are anthropogenic reasons, so it's not like only land cover change, but something else is also happening in the background, that is also creating lot of problems, which we can see the extremes. Okay, so we can see some of those things. As I said, on this work once again, so our scholar and then once again Sridhar also, like almost peak time of corona time, we worked some of these things actually. That is that also helped us to see some of the different way of understanding this particular topic actually. We will come explain on the course, we can see those things actually. So it's like we will see the how the aerosols will, you can say, the influence the weather patterns, that's sort of thing. So how they will really contribute to some extreme events, so those things we will see. So just like I'll introduce what are the aerosols and what is the influences of aerosols, and what is the unusual weather patterns we see, can we attribute. Yesterday he is saying that some of things like a dust storm, those things, right, can we attribute some of things related to the aerosols, and research study what we are carried out, scholar, and that is almost 3-4 years we carried out continuously, and we got some important things that really some of you interested, you can take up that thing further, and really some of your that area domain you are thinking, you can see that one. So first of all, before going further, can any of you know, means by this time you have some idea, or some of you are introduced some of those at least this thing, or you come across various places. What is meant by aerosols? So smallest particles which are there in the atmosphere. Okay, so they are not the exactly, we can't take gaseous particles as the aerosol, that's you have to remember. There is some, we can say, size will be there. So it is like only thing is size will vary from nanometer to even the, you can say, the micrometer size actually. That is what is the, it will vary the size, where atmosphere can hold, means whatever the gases, they can hold those particles. If they are not holding, they are coming to surface, means they can settle on the surface. So then we can't call them aerosols. So till they are in the, you can say, the suspension, they could able to sustain in the, you can say, atmosphere, those things we can call as aerosols. And so we will see, that's what is the, I can say, what you are mentioning also. So that's said like they are nanometer, like a 10 power minus 9 to 10 power, you can say, minus 3, 10 power minus 6. So here so these things actually they are really make, you can say, each and every particle which is there, once it is coming as a appearing as a aerosol, right, it will have a different influences on the so many our whatever the things like a hydrological process we are seeing, especially the precipitation time, they will influence differently. So here their size and composition will make lot of difference, and how much time they will be in the suspension, how much time they, how much distance they will travel, and how what will be the impact they will create. So they will create impact like a within a city or where the domain we are studying, or they may extend to the continents. Yesterday is explaining, right, something is happening in the Rajasthan, is creating a problem somewhere in the other part, that type of things is there. They are one of the, you can say, things like a indirect related things to aerosols only, whatever is mentioning. So here within the atmosphere something will originate because of the condensation of the gases and from the action of the winds on the earth surface. Okay, sometimes they are not directly evolved from anthropogenic action directly. Okay, so because of some you can see the favorable conditions, they may gases will condensate, that will become the, you can see these things. For example, sulfur oxides SOx, or nitrogen oxides NOx, or COx, those are the, you can say, gases form. So whenever they come in contact with some favorable cases, actually maybe the water, other things, so they will convert into the, they will part of the, you can say, they will form around a suit of the particles like a C only carbon, or like a water, which is water vapor in the form like a, the gases form. So they will also as a form as a nuclei, act as a nuclei, and they will increase the size. Then also is a possibility that become the aerosol. Previously in the gaseous form we can't call, but once there is chance that come in contact with some other things, they may also become the, you can say, part of the aerosols. Okay, so or react with the, you can say, water, for example sulfur oxides H2O, that type of possibilities, then we can say sometimes we can call them as aerosols. But this is like a one of the, you can say, the major fraction. This is like a most of the times, so they will lead to the, you can say, this coming from the biogenic or anthropogenic region. So yesterday he is saying, right, something like a whatever is carrying from the somewhere in the deserts, it is carrying to the, you can say, the sea, and there it is creating lot of, you can say, the chlorophyll action or the, you can say, photosynthesis, that type of things, right? So can you tell like a what may be the, you can say, these things, whether it is a biogenic action or anthropogenic normally? So biogenic action means like what is the thing, that type of things you may expect. So a lot of trees will be there, like actually the plants or those things. So there is a pollen, you know, right? Pollen, all the things they will carry actually longer distances. So dust means along with dust, so many things will be there. Pollens, all things. So those things will be carried a far away place and they will be settled and they will create the problem in the atmosphere. That's one thing. Otherwise, like we can see, you know, right? Some of the areas related to Delhi. So other states. So those things also will come and then they will come to the far off places and create the problem. So you can see, so the main thing is the here the mechanical action of the wind that will take it to the whatever is the available this coming as atmosphere by human or other activities. So they will take it to the different places. Okay, so it involve all these things. So that is the main thing. So they will once coming into the atmosphere, right? They are whatever the atmosphere means, whatever is the things taking place at the atmosphere, they will also influence those atmospheric process. That is the main thing. So we will see how really it will make or not. So you can't say directly, but there are yeah. So you have the very small, you can say, areas, right? Like you will with sensors you will find out what is the concentration of these particles by yeah. So this is okay, right? Yeah. So here so this one, all these things we will over a larger area, right? So like yesterday is saying about they will use in the ocean surface means they will use AVHR or other sensor system, right? So on the land surface or larger region, like maybe the continental scale or country scale, we can use this aerosol optical depth. So it is nothing but the, you can say, how if you take a column of air, how these aerosols are distributed. That will give the, you can say, the we can call as a combined factor as a aerosol optical depth. Okay, so depth more means you will get the value more. Value more means like it's like for example, you are seeing a clear to hear clearly. There is no aerosols, right? Lot of aerosols are there means in between it is a object or visibility. That way this factor will be there. So same thing like we will measure this with the satellite. So yesterday whatever the satellite systems is mentioning, some of those things like is mentioning like a Merra satellite, right? Like so many are there. Some of those things are very much useful for the studies actually. You can see what is exactly whatever satellites we can check. So this will give a complete picture of what exactly I am saying. So they come from the different, we can say, the systems to the atmosphere. So here they will take part in the some of the, you can say, other, you can say, the particles. There is a different process may occur. So there is a condensation, coagulation, or similar different atmospheric means process. What are the fluents are there? How that process will take place? Same way it will happen. So here it is all like a continuous process. Something go from the emission, reaches to the atmosphere, and they will become the part. They will size will grow, and actually they will reach to the even the clouds. They will be out of the clouds, or whenever they will, you can say, they become a sufficient size, right? They can't stay further actually. Size is gone increasing. They will not be further. We can't able to withhold. Same with the cloud also. Once it is like a coming as a rainfall, once the droplet size increases, so further also during that time also it will come down. So like a air turbulence is stopped, sufficient size there, they will come down. That is one option. Otherwise during the rain, so that also they will come down. That is called actual rain out process. So during the rain, whatever the things are there in the all the suspended things, most times we can see. That's why we can see any after rainy day, like you can see most of them say clear sky. So most of the suspended things will come down. Okay. So this is the complete aerosol, like a dynamics type of thing, like how they will come into the things, come down to the once again back to the, you can see the system, I mean like a land surface. Okay. So this is the, you can say, a aerosols thing. But these things, like a lot of things, they will lot of, we can say, the influence it will create to the different process depending upon their lifetime in the atmosphere. That is very important. So here, so they can, you can say, the of course one type of thing is like reducing the visibility, the direct effect, a direct impact we can say. The otherwise they will be in suspended things in a long time, right? It contain the pollens and other even the virus, bacteria, those things also they will be become parts since they are carrying with other things, right? Organic things I told, right? So they will create a lot of respiratory health hazards. Size is, you know, I think P2.5, P10, there are different size particles are there. So there is upper respiratory system problems, lower respiratory system. So upper, like that, so many respiratory related issues are there with those things. But that is not any of our, you can say, issues, like they are only urban related things. So, but they are more interested, which we are interested in the weather process. So they will create lot of weather related, we can say, the anomalies. So by creating like a scattering, sometimes the radiation absorbing. So sunlight is coming and hitting, right? So that is one of the main important thing, like it will all the different process, which we see the all the atmospheric in connection to the hydrological process, they are connected to that one, right? But it will all change, influence those things in a different ways through scattering and absorbing. So some, it's like they will also, like each aerosol will not behave same. The study of the behavior of each aerosol itself is a one research study. That's a different thing actually. So, but you can see the, for example, these things, right? They will act differently. So some will absorb the, you can say, heat. They will take the heat, so that they will create a cooling effect. Some what they will create, what they will do is like they will try to keep the, you can say, the heat the atmosphere. So like all like they will act like a shield, right? All these things. So whatever the radiation comes into the, I can say, the Earth zone, right? They will not allow to go back actually. So that will create the greenhouse effect. Means it's a heating effect. It's all like a different times. It will go in a different ways. So this is the, you see. So they will, you can say, create a net cooling effect. It's all like you see the both, you can say, the way it will impact. So then the conventional how it will happen. So here and one more thing, this is not only creating your temperature, but they will create more problem to the formation of the rainfall. That's one of the very important impact. Means how much rainfall will going to occur, what is the time of the rainfall. So they're all depending upon the different aspects actually, the cloud parameters, those are all called actually. So those cloud parameters are influenced by the presence of these aerosols. Like they will have sometime like a cloud condensation nuclei. Okay, so there is no cloud condensation nuclei there. They are gone providing those things so that it will create the more and more amount of rainfall in a particular area. So like you see the industrial areas. So sometimes you see unrealistic, like they are not like normal things. They are the different way of, you can say, rainfall patterns. Very heavy rainfalls for longer durations. So like a cloud burst in a particular areas continuously. That all things, something can be attributed to this type of things. So these things I think some of you are observing in the newspaper, like they will mention like this, some of these things we can see, like a very severe rainfall events that normally we can't expect sometimes in especially urban environments. Okay, so unusual rain and wind patterns. So this is like a unusual lightning cases in some of the rainfall events. So like a unusual, like most of you these things are come across in the news or not? So like anomalies actually most of times than the conventional things. So some of these things, can you tell what are the, like for example, the last case where you can see like a sudden drop, like they will say like suddenly air quality is dropped so much, where you are see some of those things. Metro cities like especially Delhi, like every wind means whether they are setting the, you can say the winter, they will say like almost alternate 2 days they say that serious problem. So similarly you can say some of these things you can see in the news like either rainfall pattern also. We can't see that type of normal rain, that type of things in a particular place. So that type of things are, you can see some of the examples which are showing in the news actually. You can see like this all like a lightning. So somehow if you think that lightning also normal thing, right? It is like a occurs actually. Lightning is a very common phenomena. But actually the study, like we can't directly say that aerosols, but you can see a lot of unusual. You see there is the study, I think some of you can see the same thing and you click. What is the problem? Okay, they are changing. Okay. So so it's like a, wherever there is a, you can see this type of things, right? Unusual activities, like so many times are occurring and so many incidents are there. So normally the lightning actually, why it will come actually, there is a lot of, you can say the charged nuclei is there, right? So why you can't say that attribute that there is a possibility that a lot of these aerosols, they have the lot of charges, either positive or negative, that may create the lot of these things. That's some of the, you can say, things that there is a chance that that is the one of the reason. Like since they, if you see this one study also, right, if you go that thing, last 50 years, maybe there, like they say that 100 years of things, there's like a changing the number of incidents. That may be like more like a activities of the human beings, like a lot of, we can say, things, but also maybe the other reasons may be there. That's what is the one of the things, maybe the aerosols. That's the thing. And of course, other, you can say, unusual rainfalls, like there is a cloud burst will be there, but still that more than that cloud burst, right, like a 1 hour, 2 hours, like over a complete night. That type of things you can see sometimes in the, you can see the metro cities. They say that that's normally we can't see in any other places. Means there is a lot of nuclei is available continuously to make the, you can say, growth of that clouds and then continuously the getting the rainfalls. So like this thing also. So these are all like some things, like some of these things including like exactly yesterday also is mentioning about some of those things. They are all like some of the aerosol related activities, like carrying the lot of dust winds, like so those all things are the some of the unusual things, right? So here okay, so you found that there is a possibility that there is aerosols are impacting, but it's like you have to prove or you have to say something is possible like because of aerosols one, it is because of this one. So I said like it is not so easy to identify or say that exactly aerosols are causing. So there may be several factors you can see the when you are seeing, but maybe you can say that when you are gone observing and you go on making a multiple studies and correlating, you can definitely say that there is something the unusual is happening and that may be the result of the aerosols. Okay, so we see what exactly the study we are proposed here and we did actually, it is completed. So here once it is like aerosols are there, right, aerosol optical depth is the parameter to find out completely to see that whether aerosols are there or not. Okay, Then like a aerosol means, yes, like it's not a point data set, right? It's not rainfall. They complete like aerial data set. We are getting from satellite. So it is like a per that different satellites will provide. We need to prove for a given area whatever you are getting and whatever is the aerosol optical depth it is providing, and it is correct. Otherwise you can't do analysis, right? So for that, like a first of all, like a looking at different satellite data and whether it's suitable for our area or not. So then we are looking at the, you can say how this you can say aerosols really creating it some temperature you can say change. That is called ADRF, like a how this aerosol direct radiative forcing, that is like a one of the influence, like either cooling or heating effect, whether any relation is there. Okay, so like a how the it is creating something on the problem on the, you can see the precipitation. Okay, and that will like a you see the once we explain what is that really something related to the precipitation and aerosol optical depth. Of course, in extreme precipitation and metropolitan cities, it is anything like a some relation is there. Okay, so we took as a part of this study the entire southern India. So like a covering like since most of the studies it is available for all for northern India, like a in the especially Delhi metropolitan region and other things, other Uttar Pradesh too. So many studies are already available. What we thought like a some of the things like a maybe like industrialization, other things are also even happening in this southern region, and how that will be better to observe that some of the cities which are available in the thing. So it's like actually we better to take peninsular India, but it is almost like a since it involved like a to see that some cities other things we took like a even administrative boundaries. It is almost like a matching to the natural boundary, like a peninsular India and other northern India. That way we took these things. So this is like a part, especially the some of you are real interested also, you can see like a what are the some of these things aerosol studies you want to make me. These are some of the important data sets you may have to look. So like a modest data, that's what exactly is mentioning yesterday. So is continuously monitoring those things, it's available actually. So this is like a MERA 2, that's also yesterday they are explaining. MERA 2 also they are continuously giving. These are the important things, they will give the various parameters, not only the aerosols related information, but other important information which is related to the aerosols. So aerosols you have to study means you need to study this something like a other aspects. It's not aerosol optical depth. You see the hourly data you can get. Okay, so you can get the cloud fraction, other important is information which is like useful for you. So you can get from different sources. So it is like a entire thing is going into the two types of the things, three types of the way the whole research actually happened. So one is selecting the data set, whether it is suitable for a study or not for the area, that is one aspect. Second is how it is like affecting the overall radiation budget which is coming for a particular study area. Third is how it is influencing the cloud parameters. Fourth is extreme events, whether it is a connected, any connection is there for the extreme events occurred in a cities or not. That way the whole flow chart is prepared. So here first we can see the how it is like influencing the this one in the study area. So like we will see the first of all the different, we can see the whatever the products which are available, how to prove that they are suitable for the thing. So how the normally anything data is there with it cutting from satellites to prove that it is a correct one. Ground truthing is required. So ground truth for the aerosols is that is a important, we can see there are like yesterday you are seeing right in the ocean they are making some instrument to collect that whatever is there in the oceans at some points, right, to prove that all the data is correct. Same way for the when come to the you can say the aerosols, this is the like there is a separate systems are there available to take that data of aerosol optical depth at different heights. One is like a aerosol robotic network, aeronet they are called actually. So they will make a different ground observations and there are some different points are there, like they will make the yesterday they are showing like some balloon experiments, they are showing some, they are explaining in the one of the places, right. That is one of the things like to tell about this event, that aerosol optical depth also it will be useful. The studies they are continuously measuring to know about this aerosol optical depth also. So here normally the ground observations from ground they are doing. So once again this aerosol optical depth we are mentioning. So this they are providing this depth, right. Once again this is like a, it is like a nothing but any other radiation. Normally you are measuring some radiation like in the remote sensing you are measuring some radiation, right. You will measure in some spectral region. like visible region, microwave region, infrared region, like that. Same thing this also, like aerosol optical depth also, you normally will get in, especially you will take a ground observation. So you will get in this particular domains, wavelength regions only, they will provide this aerosol optical depth. Okay. So this is the some established equations. So more equations as said, like you can see our papers are those things. Yeah, yeah. So actually it is the available in the satellite. They are providing the, you can say, the 550 nanometers. So they are providing a different wavelength regions. So that is like available at the 550 nanometer. Like you see that Merra 2, like we are downloading, you will come to know that what they are providing, that what are the things. Yeah, Pune and Kanpur, one of the sites means our southern India, we took that thing since to at least, like of course Kanpur is not exactly false, but to at least to prove that they are matching, so we took that things. There are some other sites are there, even Hyderabad is there, but only few experiments, even NRSC only, they are actually the conducting some of those things, but very limited data is there which it is not available in a public domain. Okay. So I think some of those things also we mentioned here, we can check. So that question, like whatever you are saying, right, this is the like aerosol optical depth. So this is like a data, one is like a satellite and other is reanalysis, means so they will do that reanalysis and they will provide, other is like directly getting from satellite and ground observations. Then we need to validate. Okay. So then that we need to prove here the how to validate, actually that is like a, once again a point observation you are getting as a this one, right. So what is the thing is there, that aerosol optical depth also will get like a 1 pixel, right. So what we did is like a aerosol optical depth, the point whatever is the mentioned. So that point we made a one buffer zone. Okay. So then whatever the aerosol optical depth we are getting per area, right. So we are averaging those all like aerosol optical depth for each pixel, which is like some 20 pixels are in buffer zone, we averaged out. Then we are comparing with the what is the point observations. Otherwise it is like a pixel means like a, it is like a resolution, right. Yesterday you saying like when I explaining JS, point means point, but when grid means it is like a some area value will come, right. So we need to do something, then only we can get exact things. So that's where we did that some of those process here. So we are did the raster processing and then of course later trend analysis, all the things to check like how it is varying. So you can see some of those things when we are explain, I will show you some of those things. Okay. So this is the one is like a aerosol optical depth with the aerometer, and then this is like a with the MODIS data set. You can see the how the, this will give you a lot of information then to decide which to go actually. So you see the Pune and with the MODIS, and then same thing with the Kanpur, and you can see here. So what is the main important observation A and B you are seeing, right. Okay, that is for the, so here and similarly the you are seeing with the, you can say the C and D, the like here, what is the important information you have to get here. So you see the B, so MODIS data set, right. So especially for this particular you can say this one, and you see for the you can say the Merra 2. Okay, so it is like a, what is the main your important observation is here. So MODIS data, so that is like a where we can get the better, and at same time, so when compared to the you can say this whatever the data we are looking for, the same thing even for the Pune. So when compared to this Kanpur is like it is giving better. Okay, means because of the like the maybe the values are like the data where they are collecting. So that too also when compared to the you can say Merra, this you can say the MODIS is the better. So that is what is the main important thing, that's where we started looking. So then similarly the you can say the, so this is like a other you can say the observation actually the this is like a other data set like a AOD data set which is available and then collected with the OMI, one more you can say the information here. So OMI aerosol optical depth getting by OMI, and then this is with you can say the same aeronet. So we see it is like a towards the, it is not coming exactly like this, right, middle, it is coming the downward toward the you can say maybe the you can say toward the satellite measurement, it's like a biased. So that's why this is also not good. So what is the our main you can say the point is, so this is like a final thing when compared to the these are three types of data sets. So what is the main observation here? Of course it is behaving better with the Kanpur, that is no doubt in that one. At the same time, the number of samples, verified, you can see the sample checked actually. So here, so this modis is better, this is the particular thing. So when compared to this one, so you are not able to get the proper things. You see like at least it is coming less than 0.5. Means there is no other data point in taking these data sets, especially to say that to take work with these things. So it is better to go with the modis. That's the same thing we verified with the literature also. Most of the time they are mentioning that modis data is best, we can be used for the this one, for aerosol optical depth measurements. Okay, this is the, you can say, after once that is proved, then we prepared like a, you see here, this is the, you can say, the in between these years like a period actually, the it's like average type of thing from this. So first 10 years, then next 10 years average, you can see the thing. So you see the value which is like a go on, you can say the value is increasing. So value increasing means like it's a 0.7 is like having more aerosol optical depth or 0.1, 0.1. It's like a more depth means like a more, you can say the visibility is not proper, so it is like a there is a aerosol optical depth is increasing. Means there are more aerosols are there. That's what is the meaning you have to get. So you see the thing when compared to the last, you can see the 10 years. Here you see this one. You see these are values are increasing here, right? This region, meaning what? Aerosol optical depth is there over a years. Like you take 10 years of average, each pixel like a level, right? Each pixel 10 years average actually. So all the values are like taken. Like other day, like our software Python we are doing, right? Climate indices. Same way here also. It's like a daily data, right? Average for the, you can say the thing, and then it is presented. So that's like a, this is the way you can see this aerosol optical depth. That will be a clear picture. There is something like a, that activity is increasing, aerosol optical depth or aerosols activity. Okay, and this is also will give the, you can say the trend, means like a, that is also will give us some complete important information for us. So like a, one is like a, two types of test we did, like a, we take the last decade, like a decade, this decade, that is called like a innovative trend analysis. Okay, so like ITA. So in that, what is the thing is like a, whether there is a shift is there between the last 10 years, means there is a less industrial revolution or that type of activities. Then a lot of things are changed, right, in all aspects. Then how the really the shift in that aerosol optical depth or not. Okay. Similarly, we can use also the use this test like the man. This is already you know like a man control test. How we can use to do this trend analysis. Okay. So here. So what is the main important thing is here, one more important point we took is here. We take, when taking, right, these are all like a values, like it's not like a rainfall, at least something to observe and something to take, and then to take as a confidence and to proceed. Actually, lot of, you can say there is a what you can call as the outliers in the analysis you do, right, in the this thing graph. A lot of outliers will be there because of few values. Everything will like look like a skewed actually. So for that, what we did is like we removed that type of some of those things. Then we made actually, that's what is the important thing. So this is the means like a, where this extreme, this 95% significant level, after of course removing the, all those things. You can see the thing here. This is the, you can say the, when compared to here, of course it is looks, you can say the very small, actually 95% significant these these in the man control test. But those values, whatever is there, so there is like a more like a value. That's what the, you can say the thing. Small zones, but more intense, you can say the value. That's what is the main observation here. Getting? So here, so you are seeing this is the innovative trend analysis. One more thing at the, you can say, particular plot actually. This is the, at a some of the point light, when we take the point value, we can see how that you can see the thing. So here like each and every pixel, so we will take and we will prepare actually. That is a different way of doing. So you can see the thing actually. So this type of things, like using the innovative trend analysis. So what is the thing here, like a first 10 years, like each and every, this is like a, all the things like a pixel wise things. Pixel wise we are looking at the, you can see the this pattern change. Means for example, this particular thing is like the variation whatever is there, that for the sense of per year, how much is variation, this is all like things are copied actually. So that will tell us like a more value, the, you can see the range is there, means there is a more drastic change occurring in the aerosol optical depth actually. So this this is like a dividing the whole data into two ops and then checking the entire trend analysis. Okay. So here Then what is the thing here? It is like a, here this is like a, everything we are not doing with respect to one point, right? We are doing spatially, right? Then how to analyze the spatially? How to make that spatial understanding? So what we did is like a, for example, like a here the entire southern India we are making study, right? Then how we can do so that all the values are there, right? So we are like a this changes, right? Like we divided into different categories. Like a more change is coming means like a limited change means negligible, like a low negative change, positive, and then very high positive change. Is like a lack of vectors, like all southern India we took, right? So it is like a, all the I can say the things it will provide, like a how much area, like a, in the terms of the lack of vectors it is changing. So you see the second decade, you see the value is like a, you are getting like a significant value, right? So it's like a very high positive change means most of the like a areas, maybe you can say that it is the change is occurring. Okay, so that's what is the thing. So this is like a obvious, that's what I explained, like you see whatever our observation finally is like a, when compared to anything, like this is doing better. So obviously that all the things we can take that one. Then of course like a where is that one? Yeah, points in where the, yeah, per Kanpur. So it's like a, you can't means like a, why I am saying is like a, even the, this is like aerosol optical depth, right? Is unlike other things, you can't get very high correlation coefficient. Since those values are like, these are all like a, depending upon the different, it's like a, whatever we are getting, right, that value, say across the domain, right, atmospheric column actually, so vertical column, and that is doing the vertical experiment they are doing. So it is like correlation, you can't get like a rainfall means we can get a more correlation. These are things 0.7 above 0.5, 0.6, that type of things are also better. That way only we did actually. It's that's what the very important thing. That is a larger aerial extent, right? It is not so like a one cell we are saying for aerosol optical depth. It is like a resolution is not like a, what we are seeing for a resolution of the land is land cover, like high resolution data. You will get like at least like a 1 kilometer by 1 kilometer like that. Means a lot of averaging will take place. Here we can't get that type of things. Okay, so it's like a, so now it is like a, how this is like a attributing to the, I can say aerosol direct to radiative forcing and connection to the AOD. Like a, especially it is called radiation budget. So how much is coming into the atmosphere, how much is going back into the atmosphere, that like a radiation budget. That will give, that is like useful for so many purposes actually. Whether it is like a agriculture purpose or whether it is like a, we are doing any like a water related aspects, evapotranspiration, these things are very important things, and they will also indirectly influence the different climatic related patterns actually. So calculating the radiation budget itself, it's very simple calculation, like of course that equations, when you say that you can see those things, like how much energy is going from different sources coming to the atmosphere, how much is leaving, how much is storing. That you can make means like you can see whether it is really aerosol's presence will create problem or not. So when we are doing this study, right, there is a special case occurred actually, like a special atmospheric system actually. So like what is that one? I will tell that one. Before that one, this is the all the, like since we have to study this means we have to make it in a different way actually. This is like a different climatic classification of the southern India. These are like a saying like a hot temperate region, like a like something called savanna, you can say temperate region, like a, there are like a different ways of dividing the India into climatic zones. Okay, so that is like a humid temperature, for example, like it's like a, our this Warangal region, like a semi-arid type of temperature zone, temperate semi-arid. Yeah, this is already available. It is like a, it is not, we are not doing anything, this is not a thing, but only thing is we superimpose the aerosol optical depth, right? So radiation budget means we will not do for a point by point, instead it will do by zone, means like each zone is a different climatic zone, right? So there the whole process, because of this for example, this is something like a some tropics, they are saying tropical savanna region, something is there. That region, the how the radiation budget will change because of this aerosol optical depth is different when compared to the other regions, coastal climate, like that. That's why that way we need to do. So this is the exactly the, what is the, you can say here we can see this whatever the data we are getting from MERA 2, right? So here, but when you are using for aerosol optical depth with the different, right? that is not sufficient for us some of the parameters to calculate. So we need to use the even MERA2 also. It's a special case actually. You can't directly only use that whatever the things I am saying about that previous satellite data set. MODIS, you have to use this MERA2 also, some of the parameters. So here this is like a MODIS, already it is there actually. So collection of temperature data from the, you can say this one, like a from whatever the IMD data set. So here we need to calculate this whatever the ADRF, and once again it is like a lot of things involved here. So this is like a different case, I told, like it is a case arised. This we thought like it really give us some insight. Normally you can't see this type of a special case. So this is like a what we took actually. That is what is the that one particular thing. Actually the lockdown period, right? It is almost like a extended for the at different places from the few months to the several months, at least like a some places like a few days and then somewhere months. So like that it has happened, and that a lot of restrictions they made, right? So can you remember how that really changed the atmospheric or this type of things actually? Yeah, since like a lot of they all stopped the all transportation systems. Okay, it is drastically reduced the how much aerosols will go to the atmosphere. Okay, so they give a lot of cooling period, means like a from the, you can say the there is a chance to settle down all those particles, right? Okay, so that is really the, you can, that normally that period anywhere you will get in the atmosphere. Now it is possible. You can't get that type of that is called pristine period actually, means where nothing is coming going into the atmosphere because of the anthropogenic activities, at least like a dominant things. That type of special case arises, right? We thought like a why can't we use that one as a important period actually. So before the that lockdown period, during lockdown period and post lockdown period. So 3 periods we taken as the important durations and we analyzed it. That gave very important aspects actually, that is also actually published on that work. And I said like at the time like a peak COVID time, right? So they also visited here actually. So we are there and we thought like we can go like this, and then we taken a lot of equations we are mentioning here. We derived at that time like whether we can make this type of things, discuss actually made. That is very interesting. You can see some of those things. These are like whatever you are seeing, right? These are like formulated like this only in one of the meetings. We formulated all the things, how to select what type of things actually. So here this is all the things actually, the this surface like a different things, right? We want to make, means it's not so easy to budgeting things. Equation is very simple, like adding and then subtracting, but what to consider? So like is all like a different fluxes coming in into the, you can say, atmosphere, coming down, and something leaving the atmosphere. Okay, so how much is there the time? So these are all like a different equations which will tell about the radiation budget. Okay, some of you interested means you can see the paper and other connected you can say textbooks or material, so that you will get exactly the all these parameters, how they are influenced in the thing. So it's something very simple that in the to explain actually, but you can see more detailed things. So like it's all like a radiation in form of the, you can say, wavelength what are the, you can say, region. So how much is coming? Okay, you will follow the, you can say, the all the plus is coming, and leaving means all you can subtract actually, and something remaining become the which is there in the atmosphere. Okay, if aerosols are not there, what is happening to that one in the atmosphere? Aerosols is there means what is that particular thing? That will give the information for us, right? It's like a some budget, like a water budget type of thing, right? Coming, staying and leaving. Same thing like aerosol budget actually. Means that will indirectly getting by how much energy is coming, staying and leaving. That will give the thing. So these are the some of the equations, you can say this one actually how we can get this short wave wavelength and long wave wavelength, and then connecting those things. Something is not available directly, what is the way to connect? These are all things are formed equations, and then we propose that this way exactly may come, and checking the things whether really it is a correct or not. So all the things. This is all like a simple thing, like a this is like a how much is the top of the atmosphere and how much is coming to the surface. So this two difference will give the what is there in the top of atmosphere, right? Radiative, you can say radiative forcing on surface. Remaining difference will give the what is there in the atmosphere. So yeah, troposphere where the atmosphere level is there, that is the thing actually. Okay, so some of those parameters are given like that actually. That is like a, we can see in the some of the this MERA data I am saying that reanalysis they are providing what is the this type of data at the so place. It is available actually, yeah. And some things are available from the this water satellite we are saying, MERA2 and MODIS. So like a cloud top temperature like that. Okay. So here these things like a what we thought is like a, so we can't really so much area you are making, right? You can't get really how that particular data we can see, right? So what we thought is like a one pixel, like a one area we will see that particular areas like a Goa and this thing Nanded. So like this we took the some of the things actually, the aerial these things like a different places. All are differently selected because of their reason. One is near to the coast, well with this well in the, you can see this one. So like these are all like a different you can say the things actually. So they will have a different type of, we can say this related to the aerosols according it is selected, and it is seen like a each and every budget, whatever the radiation budget it is changing actually. So some of the, you can say, checks we made here. So here this is like a special distribution of the, you can say, the different years. You see the different thing. So what is the, you can say, trend in this area, you can say aerosol means like a, so this is the, you can say, what is the energy like which is coming, and then so you can see this one like each and we background is the boundaries of the climate regions, and the top what is superimposed is how this radiative direct forcing this is like affecting actually. So here and similarly the, you can say, we saw this one actually ADRF, aerosol direct radiative forcing, whatever I am saying here. Because of this one, this one you see the AOD and this like a energy, and these things are also like a shown like a how they are, you can say, each period how the values are there and how they are connected to temperature. Okay. So here so then this is the like I will give you some, you can see the picture actually, the thing how this AOD one like each one you can see the, you can see the both things like you can this one and you can see this direction, and you can see this direction. So here the one is like a pre-lockdown, lockdown and post-lockdown. This is the, you can see the what is the, you can see the values like whether it is really changing the aerosol optical depth or not. Okay. So then we are taken the, you can say the whatever is the, so we here the we taken this one is the averaging out whatever the middle we are, you can say the middle at the time 2020 what is the value here, and right is the like a difference between two. Okay. So that will give the, you can say, the picture for us like a how the we can see change the this one actually means pre-lockdown to lockdown period. What may be the, you can say, the aerosol optical depth or what is the, you can say, so it is there in the pre-lockdown, you can say the, for example this is the like a pre-lockdown period, and this one is the, you can say, lockdown period aerosol optical depth. You see the that particular averaging of all the things, you can see the changes are there or not. Okay. So you see this, you can say zone, some of the, you can say this values actually the thing. So if you go for this one, this is like a higher values, that way you can see, and you can see the post lockdown period values are changed or not, higher values are there or not post lockdown. So that is like a give you an idea like a similarly the, you can say the here. So we will take the this values when you are taking the, you can say the in this particular calculation. So like it is like a 2000 to 15 to 19. So here the we made this like a difference between the these two actually. So that will give the, you can say the, you see the, you can say the differences which are occurring. What is the, you can say the less value that may be there, if you see the more changes are occurring actually, the pre and post and then other, you can say the lockdown period. So we see that, you can say, when compared to the post lockdown period and then 2020 you see the value. So that way we can check the differences. So what is the main is like a lot of, you can say, the variation is there, means there is a drop down in the, you can say, the aerosols availability, and once again rising in those things, so making the more difference in the time. Okay. So here you can the same, you can say the ADA2 or direct forcing also like how that value is there, so how it is like a change between the three periods actually. Okay. So here we can see this like a same thing like the temperature change, the, you can say this one in the degree centigrade pre lockdown. So the, you can see the post lockdown and the, you can see this period the same thing. So here what is the change? You can see the, you can say the more, you can say that you can say the changes when compared to the normal previous thing. That's what is the observation. Means temperature change more means what? There is like influence is there in the, you can say the particular the pre and post like that. So here, but what is the main one of the observation what we observed is, so during the, you can say the whatever is the, you can say things like some of the those things we say mixed type of observation. For example, so aerosol everything we removed in the atmosphere means what is our net understanding? Whatever is coming, whatever is go down, right? There should not be any temperature change actually. The temperature or there is like a previously it is like all aerosols are above, so they may create the, you can say the effect since they are all like settled down. We don't have any temperature, means temperature has to fall. Okay, so it is not so exactly happened like that. That's what is the thing, means you can't exactly the correlate like that. Maybe the various reasons, maybe like a which are there on top of the atmosphere, which are middle only settling, or they creating opposite reaction like a something like a they are behaving like opposite. I told like something like a dust which are there are the soot, so they will something like absorbing type of aerosols or something like a scattering type of aerosols. Like that, it is not like a straightforward, you can say the thing. That's what is the thing, some of the things we observed. So there is like a mixed type of things. This is the, you can say here the main important thing actually the mean temperature or the, you can say decrease in the 2020 during the when compared to the pre-lockdown turn. So when compared to the so average of this period actually. So here so we are seeing some of this type of things actually. So this is like a clear witness in that there is no this one, but that's what I am telling. So this mean temperature while ADR phase increasing and the mean temperature also increasing, but it is like a mixed thing actually. So similarly this is the other thing actually, that is what is the thing. So normally this ADRF has to decrease, right? That's what is the thing actually, that maybe whatever is already energy is trapped in the atmosphere, that is like already maybe taking time to like not getting down or cooling down actually, we can say that may be the thing. Okay, so here quickly means remaining all things I will show that quickly before I am hand over to the, I can say giving break and hand over to the Sridhar for the things. So we can see the thing here. So here how these things like we are seeing all area, right? Something like how they are really making something on the cloud. So quickly I will make the things, so instead of explaining all things we can read so that maybe give you one idea like how they are really making some influence on the thing, rainfall, or you can say the cloud condensation. So here we made the, I can say lot of this, you can say the these particular things into different rainfall regions. Okay, then we are there is a one index important for this dividing the, you can say number of, you can say the different storms actually. So then we are comparing these two things like the, you can say one is AOD and this is called actually the cloud fraction. So cloud fraction for different rainfalls is different actually, whether it is a thunderstorm, whether it is like a isolated rainfall and the scattered rainfall like that. So according this indices is different, accordingly this cloud fraction and these things are different. That thing we studied actually. So here is the final thing is aerosol or cloud precipitation, there is a connection, there are not. Okay, most of the times it is also once again a very mixed thing actually. It's like a different times, different places, it is mixed differently actually behave. So just only I will show the important thing only. So this is like a, what is the way we can take this all things we can get when you can read also later. So here once again this type of, you can say aerosol optical depth and you can see the cloud fraction. So we can't get exactly the how it is like a coming actually. So we could not see like any other thing like previously, you can't see like a direct correlation. Yes sir, you could see right here. If there is no, we can't see much correlation, that's what is the main thing. So but only one thing is see that actually when you are going here, so light rain, so moderate rain, but heavy rain, but at least which is the place where it is like looking like a more correlation or thing, means heavy rain time, events time on a cloud whatever is there and its behavior and aerosol optical depth is some correlation is there. That factor itself is sufficient for us to understand there is something during heavy rains, there is chance of that may influence actually. Okay, so this is also will provide all those, you can see the information like how these things are all like a influencing actually. So here there are like a giving the parameters like a where it is increasing and decreasing trend, and each zone also we make this type of thing like whether how it is connected or not. So let me like show you the how just like it is available in the different rain regimes and how it is like influenced actually. So this cloud fraction and aerosol optical depth. So you see the side by side like wherever there is a cloud rate and aerosol optical depth, there is a relation. That type of things we want to show here. That's where it is shown. So here similarly the other heavy rain regime, and what is the thing is like most of the areas are influencing, you see right here, that's the thing. Okay, this is the different values actually you can see. Okay, so these all things are factors you can check and then more important things, so I will show you here. So what is the observation actually, the you can say wherever there is a aerosol optical depth is there, so it is like a value is more is there is a lot of you can say the influence. Okay, definitely there is a that influence is not for the other rainfalls, especially the high rainfall events. Okay, so that anyway you can see the thing, and this is like a different things study. I said like only metropolitan cities we took and then we saw the how it is really influencing. Okay, so here we took only this for this thing. Once again the cities are, you see that they are different geographic regions and different way the aerosol optical depth or aerosols will be there. So why, what are these things? There are two sides of the another southern another whatever the region we took, and these two are the two different sides. Okay, and two different places. Landlocked region, they are the either side of the sea coast is there. So that's what is give us like a each one is a different. Even aerosols just only we can't tell. Other parameters combined we have to see. So you can see these two things, three things we took actually 4 cities. So directly you can I will show you the other things. We don't too much worry, but only thing is we studied the these are the incidents we checked actually. We took extreme events. Then directly we will show you the this one. We took all the like important thing, aerosol optical depth, cloud fraction, cloud top temperature on this one. So like each one, like if you take the Mumbai and other different events. So I seeing this thing very simple logic actually, wherever there is a same like extreme event is there, there is a other favorable condition like a cloud fraction, cloud top temperature are there. So there is a all these parameters are in favorable means there is a extreme event is occurring. Definitely that is like a more time or more intense. So means at least during heavy rain or this type of extreme event time there is a correlation with all these parameters high means other things are there, some inversely some directly proportional, that's the only thing we have to see when we are checking. So same thing like we can see some of these things. So extreme event is there, for example this particular thing. So you see this particular the you can say the aerosol optical depth and the K index and cloud fraction, cloud top temperature, these are all things are in a one particular you can say the thing. Okay, so you can correlate and you can see the same thing we showed for all those events actually. Okay, so sometimes what we observed is there is like a, you see sometimes like a, these are all things like a correlation. Okay, so sometimes we see there is like much you can say the check we can't make the correlation. So there is like a we can't make, some we could able to make. That's all the things are given here. Okay, so it's like a all the things are explained like how really they are connected together one to each other actually. So finally what is our study, very important thing is like it will give you a lot of you can say observation like so atmospheric stability is like related to aerosols presence, but related to the you can say other thing. Wherever there is a all things are clear for a unstable thing in the atmosphere like extreme events are going to occur, then the role of aerosols really there. That's the main things. Of course other all like connected things only. So these are the our main thing actually. So that's the thing actually, the of course these are all like what we thought like what we did like really somebody interested in, especially some are saying like a geography they said on yesterday when are on the thing, they are saying that they are working in different areas actually. Some of the things actually you are interested means you can see some of those things. So areas where you can really interested you can study those things, these things. Okay, so these are all things are available actually once again the public domain, so you can check all these papers really connected things. So on most of the things what we background for this all works are available these things. Yeah, any questions? Anything? So a lot of nowadays yeah. Hmm. Yeah, that's the thing actually. The means actually there is the main thing is of course wherever there is observations are we can take like a similar type of city. Pune is a what type of city it is? Landlocked city. Okay, so what type, it is a little industrialized, not so high industrialized area like that type of things. So when come to Bangalore, right, landlocked. Okay, so not so high industrialized, especially in pollution making industries. It's a different type of thing, growth, urban growth. So Pune, like that type of similarity is like we can derive like that. So one coastal city we take means we can correlate like that. Especially coastal data is problem actually main thing. But at least we can see right aerosol optical depth is proved that the main question is like whether the data which is getting from the what is that MODIS I am saying right MODIS is better, that is the only main important thing. Reference MODIS data is working or not for any particular especially for southern type of things or at least middle type of things, that one, that way, that okay. So yeah, that's a thing I think, yeah, that's the important aspect really some of interested means we can see, yeah. Any other things, otherwise I will hand out to after yeah, 5 minutes break and then I will hand out to Siddhar, yeah. Yeah. Agriculture vulnerable. Agriculture vulnerable means you are saying that means you are not studied with respect to agriculture. Yeah, means we didn't study it in that aspect actually. The only thing is that agriculture vulnerability aspect we didn't study it, especially the extreme precipitation events. One is aspect on that cloud anything connection is there like that. But definitely you see wherever some areas are shown right, change in the aerosol optical depth, radiation budget is changing. That maps are given right in the second, third objective. That we can really correlate. You can superimpose the what is the for example right now that all data sets are there right. Aerosol optical depth which is available for based on the radio radiative forcing like aerosol radiative forcing is there right, that we can superimpose on your agricultural productivity like a crop yield those things, then you can say that but increasing or decreasing, that all things we can correlate, that all things we can do, that okay. So then I will stop at this point and we will take a 5 minutes break and then come back and then so Siddhar will take over the next thing, that okay, yeah. So as just like I mentioned, like this work is done by Dr. Tarani. Right now she is a faculty working at this Polarity College Engineering. So like almost like as we said, like each period we worked in a different time period we worked and then made this one. Okay. So yeah, this is the thing. So I am stopping at this point. It's available. Yeah, I think. Yeah, you were. No, not. It is yours.
You know, you have to see their relevance on some of them are old, some of them are new, but don't worry about the location. Don't worry about the location, but just look at the process that we followed. The equation that I am talking about here is soil moisture index that we used for deriving soil moisture based drought index based on observed rainfall. I call SMI or SMDI, I think depending on the paper, but it's all more or less the concept is the same, using field capacity and wilting point from the data and then coming up with soil moisture index. This one was one of the first ones of its kind at that time, looking at user friendliness in severity, area, duration assessment of agricultural drought. So, if you have good data for soil moisture up to root zone depth, which is about 150 centimeters, 120 to 150, that is you know, ideal for crops that grow up to that deep. Sometimes it may be even shallower than that, but so it depends on the crop type. You know, if they are rain fed agriculture, not irrigated, can you imagine what would be the root distribution compared to the irrigated agriculture? Any idea? What is the difference between rain fed agriculture and irrigated agriculture? Yeah, only dependent on the rainfall is rain fed agriculture, obviously. What about the other one, irrigated agriculture? So, rain fed agricultural crops, maybe I am not coming up with a question correctly here, so I will take the blame, which is if you put the plant in a rain fed agricultural crop, they are going to be um, searching for moisture, right, all the time. They have to go wherever they can fetch water. So, some crops are really deep. They can go deeper up to even 1.5 meters like corn and sorghum. But paddy or anything that you really feed them with water all the time with ponding depth, they don't go too deep because they are getting water at their doorstep, which is the roots, you know, basically they don't fetch water going deeper. So there are differences in the way how soil moisture is measured depending on the type of crops. So you want to make sure that you have the right data for your region to interpret them. But this paper is very interesting because we were able to showcase how soil moisture is used in combination with models, not so complicated to understand, but you may be able to use this for predicting drought. Just try that first as a first paper to read, but then there are other papers that I talk about like the flash droughts, using pentats, and then using models and combination for coming up with drought index like MSDA, in this case modified or multivariate soil moisture based drought index here in this case. So, two different models, and we also compared that with GRACE data, that is total water storage, which will represent the deeper soil moisture to some extent. So, we kind of combine that, but you might be interested the latest article on this paper, which is Satish Kumar's paper on reconstructed data. Especially if you want to break new grounds with respect to combining machine learning to GRACE data, that is remote sensed, and then coming up with using you know, current data, but then going back historically. So, we built this, so we call this as a reconstructed data up to 1960. If you look at the time series that we came up, oh, this is for the whole South India again. We included Godavari, Kaveri, Pennar, and Krishna. All four of them are here. So, these are observation well sites. So, we tried to validate some of these total water storage from GRACE with observed data also, but this is a well written paper by, the credit goes to the first author, Satish Kumar. He explained all the details of the model. You might be really seeing some interesting data from this also that you can use. Again, if you are citing this paper, using this data, you can cite this paper also, but the idea behind what I am trying to show here is the corresponding, I am sorry, here I am going back to the historic data, 1960 all the way up to 2016. So, we are talking about by basin that we are building the data like Godavari, Krishna. You can just take one basin. You don't have to go for the entire South India basins. Those who are studying Tamil Nadu region take only Kaveri. Those who are Palar, Pennar, and then these two other basins, those who are studying Telangana, Andhra Pradesh region can take the reconstructed data. You don't have to redo this again. Okay, but give the credit to the author who developed this data, but it might be useful by citing their work. But all I am trying to say is they are very good in terms of correlation. We are able to prove that the predicted TWSA for the historic times when you don't have data to validate is still reasonable, because if you look at the segments here, the right side is the recent times from 2002 onwards. That agrees very well with our machine learning based predictions. So then we extended this to backward, all the way up to 1960. So then we have to give, have some trust on this data, because it is proven to be correct for the recent times. So that is the justification. So somehow you have to, build your, foundation on validation aspect of it. That's what the papers actually look at. So this might be a very good paper. So what I have done, and then this paper is one of the highly cited paper that I was talking about on Coppola based approach that I am saying. This again, some of you asked yesterday also, the parameters what to use, that peak, we kind of define all of those things here, peak, severity and duration. And then of course this is based on that run theory that we talked about. And then this has got all, I think there may be link for the code also for this. You can kind of extend this multivariate analysis. It's little complex in terms of first time reading and understanding, but what I am trying to say is Coppola based approach has been widely liked by the people because it covers the uncertainty aspect of it. So read them through. There are also, whenever you see some information that's missing, you can refer to the supplementary part. We put either the code or the data or where we got the data from, all kinds of additional information. So before you reaching out to me, if you are referring to this paper, try to understand whether or not there are supplementary materials available for the paper that we published. Most of the time we do attach our data associated with that directly into the supplementary material. Okay. So likewise, you have tons of opportunities here to explore further. I will not expect you to read all of this before tomorrow 9 o'clock. Believe me. Okay. These are given to you to take home, whatever you want to do with this. But it is for your long-term library of articles. As PhD scholars and graduate students, masters and PhD and undergrad researchers who are doing active work can keep them for archival purposes, refer them, because sometimes it might be helpful for you. Okay. With that, I am going to stop here, but I will come back to the video part later, because some global context I want to still give. But any questions on these papers, or I will post them on day 6, because I started drought discussions on day 4. That was my dilemma that I had before, whether or not to post this file on day 4 or day 6. So you will see drought files are updated from day 4 to day 6. So you refer only to day 6 files. So I will also post all these articles under day 6. Okay. So with that, I am going to actually take the last 10 minutes to talk about, or 15 minutes to talk about this machine learning based forecasting of stream flow, peak flows. Again, this is a very interesting work done by Amina Khatun from IIT Kharagpur. Okay. Some of you might know the names that are well established in the field. Effective approaches using physical models and AI/ML techniques to predict hydrologic extremes. Mahanadi, as we all know, it's I'm sorry if you guys are wanting to take a picture of this, but I think I posted this paper already on day 3 folder. You can check that out. Okay. Mahanadi in India is one of the flood prone basins, as you all know. Hirakud Dam is there. Of course, the rainfall average is about 1400 millimeters on an average, especially during monsoon. 4 to 12 degrees Celsius of minimum and 42 to 45 in December, December through June, high numbers. And the storage capacity, live storage capacity of 4,823 times 10 to the power 6, that is 4 million acre feet of live storage, and spillway capacity of 1.5 cubic feet, million cubic feet of Hirakud reservoir. So it has a cushion, but does it mean that it can still be sufficient for future extremes? That is a question that we don't know. we want to understand what is the fluctuation in the peak flows that you will have for this region given the extreme events, particularly with sea surface temperature confusing the cyclonic storms emanating or originating from Bay of Bengal region. So, it can really create some uncertainties. So, data is very important. In the past, of course, if you see the extreme events even in the last 10 years, 20 years, 2001, 3, 6, 8, 11, 14, 17, 20, 22. So, almost every other year you are seeing floods, right. So, it's a problematic situation right now. This is again basics, you all probably know this. So, I am just repeating this. Convolutional neural network has attracted global attention because it is able to replicate the data features if you just use CNN. But then if you use LSTM, long short term memory method, exhibits the ability to store the information in their memory cells for a longer period. So, if you want to really combine the data features that are captured by CNN with another machine learning algorithm of LSTM that captures for a longer time, that is a good combination. And then of course, structurally improved version of LSTM named gated recurrent unit GRU with less number of operation gates, simpler in structure as compared to LSTM. That is what people are using. However, all these models, standalone models, are not really sufficient right now. That is what people are coming up with. Just one model alone is not sufficient. Can we really come up with a hybrid model? That is the next level of thinking. So, hybridization of these models by integrating them has been a kind of a new interest right now. So, this study actually developed 4 standalone models, ANN, CNN, LSTM and GRU, and then 2 hybrid models, CNN, LSTM, CNN, GRU for daily stream flow forecasting. But again, the number of variables that we are using is dependent. Of course, I put these figures just to give you the context. We will not get into the details of it, but the paper will tell you more about it. But some of these are literature kind of paper, right. So, you can fully dive into this deeper if you are interested further. But machine learning algorithms, machine learning models, before you use, one thing that you have to be careful about. What is that? What is the one thing that you have to be careful about machine learning models? Very good. Quantity and quality. Because if you do not have enough data, it is reading from the data, right. Basically, it is going to capture the features like CNN that we are talking about, capture the memory from LSTM. If both of them are kind of truncated because of lack of data, there is no point in doing machine learning models. It will not be perfect, right. That is the basic understanding that you should have. If you do not have enough length of record of data, it is not worth your effort. These are data hungry models or approaches. The selection of suitable input variables along with appropriate length of past information is crucial. So, number of variables to predict, like drought what we talked about, like floods, we need to rely on a combination. Nowadays they call physics guided model also driving these variables, right. So, in our case what we did was we tried to come up with a combination. I do not know whether I have that slide here, but going quickly through this, the right side of this, one is CNN, the other one is ANN, the first one is ANN, CNN, and then we have LSTM and GRU. Basically, you have the same structure, input, hidden layer, output layer, and then of course, you have some combination of the gate or GRUs here, hidden layers. The hybrid models that we came up with was 2 of them, CNN, LSTM, CNN, GRU models. So, you can imagine of course, by designing a setup like this and coming up with a flow chart for process, variable selection is first important one, and then we talk about data preparation, which is going to be a time consuming process. If we are not building any physics based models in this case, but we are talking about cleaner data, quality data, that is very important. So we spend a lot of time, I think, in terms of preparing and pre-processing the data, and again splitting the time series data. I think we used 80-20 kind of split, training and validation or testing, defining the network, like how many number of hidden layers, cells, and activation functions and time steps, and then defining hyperparameters, number of epochs, batch size, and dropouts. These are machine learning algorithm syntax. You can easily get the basics by reading the available literature on those. Then defining the loss function, that's the main thing there. Training the network for sufficient period, and then validating and evaluating the model performance. This is pretty common, right? This is what we do for any algorithm development, machine learning based. One thing I wanted to say is, of course, the input parameters. I don't think I included that slide here. So the parameters that we used, a combination like precipitation only, precipitation temperature, stream flow, like that. We had in that paper we talk about 15 different variable combinations that we used. So 15 different variables of you can see we also use two different methods of correlation based and constant lagged input methods for deriving these parameters, input variables, and then 6 different models for forecasting lead time of 3 days, forward forecasting up to 3 days, day 1, day 2, and day 3. So it quickly builds up. The reason I am trying to say, what I am trying to say here is that 6 models, 15 variables, 2 different types of combination of inputs, constant based, correlation based, and constant lagged, runs the simulation options or combinations became in thousands quickly, thousands. So unless you have powerful computer, you cannot do this work. You want to make sure that you have access to maybe high performance computing, GPUs or whatnot. So that is another constraint. I mean, you cannot use your laptop and say, I'm going to do machine learning algorithm by doing all these things. You may be able to do it, but it will take probably a long time to do the work. So before you dive deep into this kind of analysis, make sure that you set the problem correct and see the resources whether or not available, whether or not you have enough data to do this kind of work. Just because it's a buzzword of using machine learning to develop some models and publish means it's not that that easy. So I would say, because you will be, when you are submitting even the paper, there may be some issues with respect to quality of the analysis with the data that you have limited, or even you may not be able to get there because your computational resources are limited. So we had that limitation. We tried to extend this work in another settings, but we could not do it with laptops or powerful computer at our desk. So we had to rely on advanced research computing at my university to run these simulations. So not for this one, but for other similar project. So now coming back, so I'm just giving you the broader framework before you dive deep into the analysis. So coming to this one here, what you are seeing is ANN, CNN, LSTM for 1 day, 2 day, 3 day forecast. I mean, up to all the 6 models that I'm showing here, combination of CNN, LSTM, CNN, GRU. Then we looked at the model performance here, measured versus observed, or simulated versus observed data for 1 day, 2 day, and 3 day. Obviously, of course, you can see based on these equal value plots, the scattered plot that you see, the data points are tightly connected or tightly hugging the one-to-one line, showing that the agreement between observed and model are tight with respect to day 1. Day 2, it is getting better. It is still not great as day 1, but day 3 is not good at all. So it falls behind, or it does not do a great job of predicting peak flow for day 3 even with all these combinations. But CNN LSTM is little bit better for, I mean, I am not showing all the metrics. The paper has all the numbers, you can refer to that. But all I am saying here is that by cursorily looking at this graph, what you can say is CNN LSTM and CNN GRU hybrid models are doing better for predicting peak flows based on these two statistics that what we came up with. So again, um, looking at the peak flow for 1 day, 2 day and 3 day, what you are seeing, this is for testing period, that is for training and testing, this one is testing. What we are seeing is 1 day very tightly matching all the 6 models. Maybe one is probably little bit off for first day discharge wise, but then for 2008, but 9, 10 and 11 you see pretty good correlation for day 1 simulation of all 6 models of peak flow. So that's a reasonable thing to expect. Within 1 day you can predict. You remember I was telling, if you know your things as of today correctly for temperature, you can predict, let's example this temperature, you can predict definitely with much more confidence for tomorrow, but the day after tomorrow you may not know, or 3 days forecast you may not be 100% accurate. So that's what exactly we are saying. Day 1 is always better. Day 2 all 6 models are kind of still okay, but day 3 you can clearly see they are kind of, some are doing better, some are, I mean, not doing better when it comes to peak flows for the same period 2008 to 2011. The takeaway of course from this is CNN LSTM and CNN GRU is better for up to 2 day lead time, but the selection of input variables will be really critical. Out of 15 different combinations, I don't exactly remember which combination we used, the one that I am showing here, but it is 4 combinations: precipitation temperature, daily discharge at the outflow or the upstream, and one more variable that I cannot remember now. So all those kind of combination of variables played a better role than having only precipitation temperature. Consideration of discharge points upstream of the watershed is very important because that's where the runoff generation starts, and your target point would be outlet, right, basically your downstream location. But you can, if you have multiple points, you can use multiple, or you build the model for a few locations or one location, transfer to other places. There is another option for doing the transfer function also. Developing CNN LSTM in this case does a good job for Mahanadi. It may be the same for any basin that you look at, Krishna Godavari for this case, but some effort to to really see whether or not machine learning works for it. It could be just inflow prediction using machine learning algorithms. It doesn't have to be peak flow. I mean, peak flow is an example, but it could be inflow. That means you can even have a combination of physics guided models included in them. So variety of ideas, approaches that you can have for building machine learning based approach. This paper I have posted. I think that link also may have information on the code that's available, but if you are using this paper, cite it, and maybe if you need any additional information, either you can write to me or to the first author. There may be some options available for you to help. Okay, questions on this? Yeah, yeah, I think so. I would like that. Hydrological models, you don't need HPC unless you go for WIC model for a large area, because it's a gridded model. It needs all kinds of, and depending on the number of years of simulation that you want to do, but you can do still better with if it's a VIC model, it's a Linux model, it's not a Windows based model, so you have to run it in Linux version. Uh, Reasonably okay, you don't need HPC for that, but if you're using machine learning for the same scale, definitely you need a powerful computer. A cluster would be good. Okay, if, okay, provided yeah, yeah, upward or uploading and downloading only thing is yeah, because you may be able to run it and store it there, but if you want to bring it down, R squared I think is the one we used. 0.7 and above, yeah, is better. But I think ours was reaching even up to 0.85, 0.9 some cases. Mm -hmm. You are asking the basic algorithm of how they are different, right? Don't ask me that question because I think I didn't do that. Yeah. Well, store that question. I think this will be covered on Monday when they are talking about different machine learning algorithms. Um, I think I think Dr. Venkat Reddy will start with that. Maybe if that's not covered, then we can talk at that time. But I think this paper also may have that information. But that graphic that I showed will have even the differences slightly explained. But I don't know if they are basic stuff, it may not have been included. But roughly speaking, I think for each of those graphics, there was some explanation attached. So please look at that and see if you can discuss with me after that, after you read those. Yeah. Mm -hmm. Mm -hmm. Yeah. Yeah. Oh, why is it needed? Oh, why means obviously you don't trust your model. Once you build it, you have to validate, test and validate. So uh, certainly keep some data that is not used. Otherwise, it will not be a perfect model that is available to you. That percentage split is depending on the length of records. I would prefer to have longer period even for testing also, but we were constrained with the limitations. So we wanted to come up with a better model. So used most of it for training the model. So you can, I mean, you have to explain in any analysis. Don't go beyond the literature suggested anywhere from 70 to 80, but if you go beyond that, they may have some questions in the review process when you submit. But 70 to 80% if you use for training and then remaining for testing and validation, that's fine. You can do that. Oh, that is true. Another thing I forgot to mention, good point. Model can overfit because it's getting confused with so much of information that you give, right? It will capture all kinds of information that's available to it, and then finally it will be like your masala mixed up and nothing you will taste distinctly, khichdi, right? Yeah. Yeah. That I don't remember, but there is a 15 combinations. There is a table 2 or 3 that you can refer. I think we tried all combinations. PT, stream flow up with upstream gauge station, and maybe other combinations. But important ones, yeah, I would say if it's peak flow, certainly P, T, and anything to do ET also I think would be of use. Um, but it depends on the question that you are asking for a machine learning model to use. What is your ultimate variable that you are predicting? So that will drive what are the important ones. Yeah, runoff, I would say all water budget terminologies that we are using, if you have access to those data, use most of them. Yeah, but fitting with the data will help you first. I mean, trying to fit the data with the different combinations will tell you which one is, I mean, that is the beauty of machine learning. It's like your, robot, right? I mean, it does not think, I mean, it thinks, but what I'm saying is it does not think like humans. It takes all things into consideration and gives you the best fit. And then you can interpolate or interpret what it tells, whether or not it misses some of the variables or not. You feel comfortable by adding more, then you do that manually. But I would say trying with different combinations even mechanically without even thinking is possible with this kind of approach. I want to save the last 5 minutes at least for showing the last part of one of the videos, but maybe that is just to give you an idea. It is again another continent. We talked about North America for drought, we talked about Australia down under, so two extremes, two corners, but then in the middle, African continent. For India, of course, you are all familiar, you are much more familiar by witnessing yourself firsthand of drought. Wherever you are coming from, you cannot say that I have not seen drought. You must have seen at least once or twice in your lifetime, right? Whichever region you are coming from, north or south, west or east. So with that, oh, by the way, I wanted to show something here. I did quickly, but time is running out. Let's say if I can finish with this one and Uttarakhand, Chamoli, I want to show some photos. We used this small drone. We flew this over Malawi. Yesterday, you remember in our presentation, they talked about structural level information they are giving when the storm surge or sea level rise entering into the neighborhoods and inundating, and the scientist that was describing, they can go first story building, 2-story building or 3-story building, and they will evacuate the ones that are in the low levels. We did that kind of work couple of years ago for Malawi, tin versus thatched roof, and this is a combination of SWOT model, drone data, and then we kind of mapped which ones are vulnerable for floods. It's an interesting paper to refer to. So we are able to kind of use the drone technology, hydrology model to come up with making some decisions about how to help people for deciding on the disasters, helping them during the disasters. The next disaster that I am going to talk about is the Chamoli land or glacier collapse that happened 3 years ago during COVID. That's why we all wear masks. You could see we got this drone from, we have Virginia Tech has a branch in Chennai, Virginia Tech Chennai Center. So we took that all the way to the Himalayas. This is Joshimath in Uttarakhand, few kilometers away from Rishikesh. I may be mixing up the geography. Those who are from that region, excuse me, but I think it's basically east of Roorkee, Haridwar, Rishikesh, and then going all the way to Joshimath to Chamoli, the mountains. So we took this heavy stuff. It's a nice collaboration effort by all the scientists, drone pilots. 17 of us went. We went to the Ganges in the upstream areas. This is a scientist, Dr. P.K. Mishra, helping to collect the data on velocity. We were collecting the velocity of the river. This is the dam that I was talking about, the thermal or Tapovan gates. One of the gates broke open or breached, and it destroyed the area, and 73 plus people died. The pillar you can see there, it's really a huge one that's totally blown away. Amazing. And I tried to even measure the diameter. Can somebody tell me what is the diameter of this? 3 meters. It was somewhere close to that. Yeah. So, and then they built some temporary bridges right now, and then these are the scientists. This is Dr. Deepak Bisht from NIH, very active scientist. But we all collected soil samples and then took flow data. We are trying to fly the drone, collect some data. The work is still not completed, but for disaster modeling, you need really ground truth, ground data for validation, or even to understand what has happened exactly. So sitting in front of computer is one thing, but actually going to the field and collecting information is very helpful, whether it's floods or droughts. We'll stop here and then continue afternoon, but I'll show you a quick video. Maybe if we can tell them to stop, I think that will be great. Thank you.
Right? So is it fine? I think so. We'll start a class. So what we have done, calibration we have done. We are taking some events. So we have calibrated that, and using those calibrated parameters, we have did validation. So if the performance was good in both calibration and validation, using those parameters, we projected the future. We projected the simulated flow for the future period, right? Now, in this class, we'll see with that future projected flow, so how the flood is moving. Is it inundating the places nearby or not? Or is it like what is the depth of that flow? This is the first. So this is called, we have seen in the last class, precipitation, how the infiltration classes. So we have three methods, right, to convert precipitation to runoff. Loss method, which calculate all the losses, infiltration loss, canopy interpretation loss, all those losses. Then the transform method will give you the direct runoff hydrograph. After that, this Muskingum method will give you the direct runoff hydrograph, routed direct runoff hydrograph. Then if you add base flow to that, you will get stream flow. So now our interest is this. So after reaching the water from surface to the stream, so our interest is to know what is the depth of that stream, what is the depth of flow in that stream, and how extent it is going when the peak is coming. Okay, and how on which velocity it is moving. It means how fast it is moving in the stream. So these three we are going to address now. What is the depth of flow in the stream? What is the velocity of the flow? And at what extent water is moving. So I'm just triggering some points before I'm going to continue the across. So this is the watershed. So all those are water coming and entering into the stream, right? You just take that small part. I'm just keeping that here. So this is a plan view. Okay. So these are two cross sections, AA and BB. One is cross section view and another one is profile view. So this in the cross section view you will get to know the depth, means top width, all those geometry you will get to know. In the profile view you will see the slope. You can find out this is the way you can find out the slope, and also we can find out the velocity. So coming to across, so to find out these hydraulic parameters, depth, flow and velocity of the stream flow, so we require hydraulic model. So across is one of the hydraulic model. So which is Hydrologic Engineering Center River Analysis System, which is developed by same US Army of Corps, and it is designed to simulate and analyze the river hydraulics, and it is a key tool for understanding the water levels, means depth, velocities and river hydraulic parameters. and it is openly available. It is open source, and in using HECRAS we can do 1D 2D modeling and 1D 2D interaction modeling. I'll tell you what is 1D, what is 2D, and also you can perform both steady and unsteady. Steady means what? The parameters are not changing with respect to time. Unsteady means the parameters are changing with respect to time. So whatever the flow we are getting from HHMS, that flow is changing, right? We are getting that 31 days event duration, the flow is not same. With respect to time, it is changing. So that is unsteady flow. So we will do both steady flow and unsteady flow in HECRAS. And this is, we are limiting to 1D because it will take more time for 2D and all. I'll explain. This is just I just kept my handwritten this one. Don't mind it. So I just want to explain. See, the first one was plan view of the river. So water move along the direction of the river, right? So then water will, like slowly water will increase the depth in the stream. Then if it reaches the maximum level, then water also will move into the floodplain area, right? So water is moving along the direction, or also it is coming from in the z direction from here to here, and also water is moving in another direction. So the water is moving in 3, not in 1D and not in 2D. But anyway, this direction will come only when fill this water. So we are mainly focusing on along the x direction how the water is flowing, and in the y direction how water is elongated. So these two we will consider. This is same. It is a difference between 1D and 2D. So if you focusing on only along the direction of the river, then it is 1D. If you are focusing on both along the direction of the river and in the in all the directions, longitudinal and latitudinal direction, if you focus, then it will be 2D. Okay. Same. In 1D HECRAS, the flow is assumed to be vary only in the longitudinal direction, means along the river, and at each cross section, the flow is assumed to be same, uniform. And then in 2D HECRAS, the flow is allowed to vary in both longitudinal and latitudinal directions. So this we can done by creating some mesh. I will tell you. So when to use 1D and when to use 2D. For example, in your case, if you want to focus on how the flow is varying along the direction of the river, then you have to go for only 1D. For example, if you are focusing on the river study, river basin, if you want to see like along the river how the flow is moving and what is the inundation happening just in the floodplain area, then you can go with 1D itself. Suppose if you want to do urban floods, suppose urban drainage management, so how water will move from higher elevation to lower elevation. It won't only move in the river, right? It means just in the one flow, right? So wherever the elevation is there, elevation less, so water move in all those directions. So if you are looking in that aspect, to go for 2D. If you are looking only in the river, along the direction of the river basin you are studying, then it is 1D is sufficient. Okay?
Sir, it is across river and distance. Will it be applied for urban flood only?
Yeah, that's what I am telling. Across can be done using 1D and 2D. In some places you will get to know the river is also going within the main city, so you have to do both 1D and 2D. That both both also you can do. But interaction is also there in across. You can perform 1D 2D interaction also. Yes. Yeah, that's what it was upgraded. Initially it was 1D was there, then it came to 2D, then it came to 1D and 2D interaction also. So this is the interface of the HECRAS. Understood, right? What is 1D, what is 2D, when to use 1D, when to use 2D. So this we can done using this software called HECRAS. So this is the interface. So these are the three main, I can say 3 main windows in the HECRAS. So this is the main interface. In this you will get so many options. So one of the main option is creating geometry of the river, geometry data, and next one is, see, we took, that is also, it is a subset of the geometry, RAS mapper. So what we will do in that is, we don't know exactly like how the river is going, right? So in the using the RAS mapper is nothing but is a kind of GIS layer. Okay, you can upload your DEM, or you can upload either in there. You can also see Google satellite maps. So if you see here, this is Google satellite map. So in the Google satellite map, using this, we can identify that this is the river. This is how it is going. So based on this, we can what we can say, we can draw these lines like how the river is going. All those geometrical data. This is called geometry of the data. We can draw using RAS mapper. Okay, so that will reflect in this geometry data. We'll get to know once we are doing. You will get to know clearly. So same like in the HMS also, we are having four main files. Here also, like first one is project file, which contains the information about the project, and second one is geometry file, which is very important. Here you will get the what is the river cross sections and how many cross sections are there, what are the width of the river. All those geometrical information of the river will be stored in the geometry file. When you suppose after creating the project, in your folder you will get all these four files. So the flow and study it is one of the important file. So here we will mention the information about our discharge, like either you want, if it is a study flow, we will mention that study flow information, that value. For unstudy, if it is unstudy, we will mention about our unstudy along with some parameters are there. I will tell you. So all those information will be stored in this file. And this is plan file. The plan file is nothing but you want to run, like it is something like the control specification file. In this, that information like from which period to which period you want to run and what parameters you want to use, all those information will be there. Yeah, this is one of the RAS mapper explained already. Yes. See here in this RAS mapper, this is how we need to draw the lines. So this blue line indicates center line of the river. This red lines are bank lines. Just it will so that model will understand this is the bank of the left bank and this is the right bank. So it will calculate the distance of the left bank and right bank. And this line indicates the floodplain area. So how much floodplain area is there? What is the probability of so it is just our assumption flood may go up to this line. So that line we need to draw. It is an approximation line. So if it is flood is going to that point, it will go. Otherwise, all these geometries we are drawing so that when we throw the flow here, it will reach up to these cross sections only. For example, if you are limiting these cross sections up to here, you will get the flow up to here only. That's why when you are drawing these lines, it is better to create with more gap, so that till that flow is there is a chance of going there. The flow is going there, it will predict. Otherwise, it will. You will see when we are doing. You will see that. So understood? Blue line is center line, red line is bank lines, and next line is flow path. Flow paths. So the maximum extent of flow can go, and these are cross sections.
Excuse me. Why we are dividing into so many cross sections?
So see, what HECRAS will do is it is like how we did in HHMS, dividing entire area into subbasin. So it will do all the calculations subbasin level, then it will go to the next slide. Same. It will identify the depth here, then it will go here, then it will go here. So these many times model will run till the last point. So how many cross sections are there? That much accurate it is.
We are giving the streamline. We will give it continuous or we will give channels and indefinite streamlines and sections also.
No, we will give continuous.
Continuous streamline. Then for the cross sections it will.
Yes. When we are doing it, we will let you know. So this is about just center line. That. So, but the cross sections, when you are drawing cross section, this cross section should cross all the lines. Okay, and if you see here, when you are plotting, when you are drawing these cross sections, it should touch all the 4 lines, and this cross section should be perpendicular to the main river. Try to keep it perpendicular to the main river line and center line. And always I am saying, if I am saying, for example, this is, if I am standing here, this is my upstream, that is the downstream. So this will become left, this will become right, right? So when I am saying left bank means, assume that you are in the upstream side, this is left bank. So if it is a upstream, so this will become left, that will become right. Okay?
Sir, all the cross-section lines will be perpendicular?
Yeah. You keep maximum, try to keep it in perpendicular to the main river. And they should not intersect each other. Okay? Yeah. So after running it, we will get the levels at each cross section like this. At each cross section, what is the water level, what is the depth, what is the extent, everything you will get to know for each and every cross section. And this is the unstudied flow, how to give. This step you will get to know while doing. And finally, you will get the result like this. Okay, how the flood is inundated the places here. Okay, understood? And I want to tell you one more thing. Small thing, don't confuse. So how it is? Suppose we are giving flow, right? So how it is getting calculated depth at each and every cross section. So it uses Saint Venant's equations, both continuity equation and conservation of mass. This continuity equation is nothing but inflow is equal to outflow. If any losses are there, that one. Conservation of mass will try to what we can say, balance the forces. So our one is it will go through water will move through gravitational force, right? So what is the opposite force? Frictional force. So it will balance the both. So in simple, what we can say like this. So your continuity equation there, right? So for example, Q equal to area into velocity, right? So Q equal to area into velocity. V is nothing but velocity. It can be calculated by using Manning's equation, 1 by n r to the power of 2 by 3 h to the power of 1 by 2. So, but I'll tell you one thing, like how it calculates. It is important. So this is the point. Yesterday in the HMS, this is outlet. If you see that full figure, you will get to know. This is the outlet. So here we simulated the flow. So now we will give input here. So it will come like this. Okay. So it will but we don't know at the end what is the flow, because when we are doing it, so we have to identify the boundary conditions. So first one is for upstream flow. Downstream we don't have any flow, right? But what we will do, we will apply normal depth concept, means we will assume that the flow is moving normally, means uniformly. So we will assume that whatever the water level here at the downstream point, they are following the bed surface slope. Bed slope here, so we will assume that bed slope is equal to the friction slope. So from there, we will identify the friction slope, S value. So if you keep that slope value in the Manning's equation, 1 by n r to the power of 2 by 3 h to the power of 1 by 2. If you keep S there,
Velocity.
it will give you the velocity, right? But we don't know the depth, right? We don't know the depth. So velocity is a function of depth. Because V equal to 1 by n r to the power of 2 by 3, r means radius, hydraulic radius, A by P. But area, we don't know. You just know the width of the river, we know. But depth of the river, we don't know. So velocity is a function of depth. So, but we are assuming that it is flowing uniformly. we'll know the Q. So Q equal to area and velocity, we'll find the depth. So, but that depth may not be, for example, but it is not uniform, right? But it is not uniform because the energy at one cross section and energy at second cross section is not same. In between, that loss of it will be there. So what will happen? It will back calculate it. So here you will get Q. It will again go back to the first Q. If it is matches with the first Q, then the depth is fine. Otherwise, it will again come to here. It will change the depth. So it will. So this is the infinite process. Something finite. This is finite difference method is happening inside. So that is what it will happen inside.
Considering the meanders, we need to undertake the angular velocity also, right?
Yes, yes. Momentum also it will consider. Yes. So that is what happening inside. So until it is matches with the first Q, it will try to iterate that many times. Then it will throw you the final depths. Okay. Based on that depth, we'll see the inundation. Okay. So now we'll start doing it. So all of you open across. All of you open. This is the small window. Don't. That's it. Okay. This is a small window. The first step is what? Usually, what is the first step? You need to create the project, right? Same step. First step, creating the project. For that, just go to File. All of you follow with me, okay? Across will get so many errors. Just follow with me. If you are stuck at any point, immediately you call me. I will come and I will do. Okay? Go to File. Create new project. Click on New Project. Yeah. Here in this box, see here. Here you can choose the folder where you want to save the project. Okay. Here there is option. You just click here, save it wherever you want. Just select that folder. It is better to save where the data is there.
Last time's data only.
Yeah. Same last class data only same. I'm not using anything. Same last class data only. So, if you want to create a folder here, you can create it by clicking here. If you want to create it. Otherwise, it's fine. You can directly save in the main folder. So after that, after selecting the folder, just give the title name. Don't give with spaces. Always any model, better don't give any spaces while creating the name. So I am giving just T1. Just click OK. Yeah. If I am going speed, you just ask me to stop. I'll stop. Just if this window is coming, just click OK. Just click OK. So all of you reach here. So next step, actually mine it is already in SI units. So if I think yours is in US metric, huh? US customer units. So to change it into metric, go to options. Go to options. Go to options. Here option is there. Unit system. Change it to system international metric system. Just click on this. If you want to click select this, next time onwards it will come in the SI units itself. Okay? Just click OK. Now whatever the units coming from that, whatever the data which is coming that across, it will be in SI units. Options. Now you check the right corner, it is in the SI units or not. Right? All of you reach here. Just save it. Just save it. So next step is creating the geometry. Okay? So to create the geometry, click on File. Sorry. Click on Edit. Click on Edit. Click on Geometry Data. Click on Geometry Data. Just save it. Save this geometry, empty geometry. Go to File. Go to File. Save geometry. Just name it as geometry. Yes. Save geometry. Click OK. So in this geometry, here we need to draw the river center line, bank lines, and flow paths, cross sections, everything we need to draw here. Previously, when the HECRAS started in the first version, there is no GIS layer inside the HECRAS. Now, in the newer versions, the GIS it was included in the HECRAS. So that is nothing but RAS mapper. So using RAS mapper, we can draw all those lines. Then all those lines will be visible here. Okay. Otherwise, like it is difficult to know what is from where to where the river is going. All this. So using so just close this. So we are drawing the geometry using the RAS mapper. Okay. Here, this option, this layer option, that is open RAS mapper. Just click on that. right? All of you reach here. Click RAS mapper. So it is like our GIS layer. So first to see all our rasters, we need to set this two projections. Okay, we need to assign coordinate systems to this. So first step is setting projections. So for that, go to project. Arun. So click on set projection. Click on set projections. Here we need to choose in the HMS what we did, we mentioned, right? 43 and like that we mentioned. But here there is no option like this. So what I have done is we need to create a shapefile with projections. So whatever the HMS file we have that we developed, I told you, right, we can export the shapefiles from that HMS. In the same way, I exported. So if we export any layer which is already projected, so the exported layer is also same projections. So we are just using that shapefile. We are just taking the projections from that shapefile. Okay. I already given you that shapefile. Go to file. Go to file. Not this one. Whatever same. Across also will give you one .prj file. Don't select that. Okay. Go to Netravati data. This PRJ file. Just open this folder. Select this .prj. This one we don't know. What is that? Okay. I think he has shared now that projection file in the WhatsApp. You just download that. See, when you create any shapefile, it will be with multiple files. .prj, .shp, .su, something, all the files. In all those files, we are just taken .prj. In that file, it will be all that projection system will be there in that. So we have chosen. I just take only that and I just copy paste it here. Okay. This data is not with you. Any shapefile which is having 43 and not, you can use that. This file is not reached to you. I shared it. Download it from WhatsApp group. It is there in the. Otherwise, there will be one more projection file in the yesterday. Like last time you have run the HMS, right? So in that also .prj file will be created. You can use that project file. Okay. We just taking the coordinates. Okay. Anyone got stuck here? Done? Done? Not done? Yeah. Okay, we done now? Got that file, right? Understood, right? Why we are selecting this? Don't have option to enter the 43 now. We are just taking the shapefile which is having the same coordinates. We are just assigning it. click on open, sorry, select. So here you will get to know the projections of that shapefile, 43 north. Okay, I just simply assign the coordinates. Done. So click on apply and OK. Click apply and OK. Automate files. All of you reach up to here. So now we have assigned the projections to the map layer. So now we need to give the DEM to the model. Okay. So to give the terrain data, go to project, click on project. Here option create new raster terrain. Click on that. Create new raster terrain. Here this plus symbol it is not add data. So just click on this plus symbol and choose the DEM file that is there in the Netravati data. Just choose the DEM file, raster file. Okay. Next click create. Now it will take a couple of seconds to load the DEM. So terrain came. Till now no error, right? Everyone got terrain. Just close this window. Now you can see this is our study area. Yesterday using HMS we have simulated the flow till somewhere this point, right? So we don't know exact the location of that point. So to identify the location we have to add that outlet shapefile here. Okay. So for that click on project. Click on project. Here option is there, add layer. Click on project, add layer. Then choose in the Netravati data, Netravati outlet. Choose this shapefile. Open it. Now you can see in the map layer where the outlet is there. So in our case that is upstream. Now we are looking at the what is happening downstream of that location. Okay. So what do people do? Zoom to that particular location. Zoom the map. Let's see here. Zoom like this. Project and last. positioning here. Positioning here. From there I can maybe version 6.1 है. 6.1. Just all of you reach here. Now we'll add our Google satellite map and see really that the flow is matching with the same or temp or not. Okay. To add that Google satellite image, just right click on this map layer. Right click on map layer. Option is there, add web imagery layer. All are connected with internet, right? If internet works, then only it works. Okay. Then choose Google satellite. Google satellite or Google map. Click OK. See, our point is here, right? So if you don't have that, like, you can also using this also you can draw the center lines and flow paths. Understood? How to add Google satellite map? So just right click on this map layers, add web imagery layer, just select Google satellite and click OK. So this is important after running this model, you will get flood inundation map, right? So you can able to see like water inundation. Okay. As of now, you just uncheck it. Uncheck it. So next step is to draw the center line of the river. Okay. To draw the center line of the river, see here. 1 minute. First to see how I am drawing. Okay. Then you will do it. Otherwise, it will be some. You have to do it very slow. First time you are doing. So first you see me how I am drawing. Then you do it. Okay. So to draw the center, to draw the center line, first activate this, click on geometry. Then the first option is reverse, right? Yeah. So just we need to right click here, add geometry. See here. Okay. You have to draw the center line like this. For example, when I am drawing, it went like this. Okay, simple. You can just click Ctrl Z, it will come back. Okay. So just click here, reverse, geometry data. Now it is already started. So just click somewhere below this point, not above that point, because we have the data below this point. Okay. Right click, edit geometry, then start below this point like this. Slowly draw the main river it should pass through the center. No. Click on river, edit geometry. Right click, edit geometry. Then slowly draw up to that point. Zoom in, sir. These lines are important. Draw carefully, okay? Mostly errors will come here only. So, yeah, there is no like end point we don't know. You can stop somewhere here. Okay. Is it fine if you went forward also? Is it fine? We don't have end point because we don't know the downstream boundary. So you can drop it somewhere else. After drawing that, just double click it. It will ask you to save to each one. Just click yes. Okay. Yeah. See, it should be only one reach. River one, reach one. Suppose if you if you give the brakes, now it will show you reach one and reach two. Okay, don't give brakes. It is a continuous line. Okay, but it is continuous. It's not on. River one, reach one. Okay, save it. Click OK. All of you reached here. Anyone any doubts? Any stuff? Okay. Zoom it to the right corner. You just zoom it down. Still zoom it. So shall we proceed? So now that's what you cancel it again. It should be continuous reach. If it is creating twice, means reach one, reach two, you just click Control Z. It will come back. It should be only one reach. Reach two means again it is the second river. No. It is fun. Actually, we good point. For example, if any tributaries are joining in between, so that you can consider it as a reach 2. So again you have to draw the center line for that tributary. Suppose for example, when a tributary is joining here, okay, again you just click or draw one more center line. So that will be act as a reach 2. So those two we can connect it to junction. Okay? Understood? So now we have drawn this center line, right? We need to save this. So to save this, just right click on this. It is asking stop editing. Click on stop editing. It will ask you to save. Click S. Okay? Then after saving, it will be in blue color. Okay? All of you reach here? So now we have drawn the center line, right? Next step is to draw the bank lines. So that model will understand what is the left bank width, right bank width. Okay? So to draw the bank lines, here, right click here, same way. First see here, I am drawing it, then you practice, then you do. So edit geometry, okay? It should come close to this point, this layer. Understood, right? By seeing this, you will get to know, right? This is the bank line. So draw the same line, like that. See here. Okay, left one is done. Just double click it. Again, you come to right one. Same way you can do it. And then double click it. Do it slowly. Same, if you are done any mistake, you just Control Z, it will go back. And forgot, always draw from upstream to downstream. Okay, don't draw from downstream to upstream. Always draw from upstream to downstream. So the model will calculate the slope of the each cross section. Next we are doing that step. So it will calculate the same. In the same way it will calculate the slope. So after drawing these lines, model will calculate the distance between the center of the river to the left bank, center of the river to the right bank. Yeah, save. Right click, save.
Save for
Stop geometry, stop editing, save. Note two lines should intersect. Okay? It is done. All of you reach here? Yeah. For example, if you want to edit after drawing this line, if you want to edit, if you want to adjust the line little bit, just click on this option, edit features. Okay. So after clicking this, just select which line you want to edit. Just click on that line, double click. So all those connections are enabled. You can just adjust. For example, this you want to adjust, you can adjust little bit like this. Okay. You want to adjust, you can adjust little bit like this. Then after that, you just double click it. Okay. That adjustment we can do. Don't save it. Again. That's one more thing. It should be a continuous line. It should not be any breaks in between. Okay? If it is break, again it will throw error. All of you reach here? So our center line is done. Bank lines are done. Next, flow paths. Flow paths, nothing but we need to draw the lines considering the floodplains. Okay? Just save these lines. Stop editing. Just click save. So these lines are saved. Next one is flow paths. Same, right click it. Edit geometry. See here. It is an approximation line. Okay. So we are assuming that Up to this is the floodplain area. First, always better try to draw from left to right. Because it will always calculate, model will calculate the first line was left line, the second line was right. So it will assign the distances in that way. So double click, same. On the right also same. Just double click it. That's it. How to draw the geometry. That's what we are assuming that. So if you open the Google satellite map, so till that for every river they will say that from here to here this is the floodplain area. So based on that width we can draw those lines. Okay. I will show you. Like if you draw the flood, immediately when you are drawing it should be meaningful. Wherever the river is going in the same direction, flood plan is also just it will also follow the same river path. For example, if you got that shapefile from from government departments, you may get the floodplain area shapefile. So you can import that shapefile, and you can, by seeing that shapefile, you can draw those lines. Okay. This is upstream. This is our prime stream. So this will be the right. This will be yeah, you will see the direction of the flow. Then we have to decide left or right. Yes, yes. All of you reach it up to here. Save it. Same. Right click. Edit. Stop editing. Stop editing. Save it. Okay. So next step is drawing the cross sections. So there is no limit. We can draw only 5 cross sections, 6 cross sections. It is not like that. For example, if you want to assess, when you are doing this for in a river basin, if you want to assess what is happening in each and every 500 meters, then you can draw the line cross section at each and after 500 meters. Okay. There is no rule, but how many cross sections are there? It will calculate for each and every cross section. till the downstream. So just see here, first see here how to draw the cross section. So the cross sections, two rules are there. First thing is should draw from left to right, and it should intersect all the four lines, all the lines, and try to draw that line perpendicular to the center line. Okay? All these three should be keep in mind and draw. First see here how I am drawing, then you draw. Okay? Same. Cross sections, keep this. Right? Any geometry. After drawing one cross section, you just double click it. Again. Yeah. Understood? That cross section will give you the shape of the river. We'll assume that depending upon the cross sections only, nothing but it will flow, can't go beyond these lines. So after getting results, you will get to know that whatever even the indentation is out of the cross section, it won't show you. That's why when you are drawing the cross sections, you have to try to cover the possible area of the flood. Okay? We'll see. Now, when we we are creating cross sections by drawing this line. Yeah, so once you draw this line, then taking help of them, the cross section will form. Not immediately. You will get out. Yeah. That's what I can get. It's all we should require the information from the river. They will tell you that this is the possible flood area. So based around that distance, we draw the flood area. Based on our cross section distance, flood will go up. That's why when you are drawing cross sections, it is better to draw the full length. The maximum length, nothing will happen. So till that point will go. Water is moving where up to which distance water will go up to that point will go. But if you are drawing less cross section, water will be moving to the point. We need to give in the master format. Actually, what will happen when you are drawing this cross section, right? So at each and every point, it will require the elevation. So you have to get those elevation in the format of master. Them only. Point elevation. Understood, right? The importance of cross section.
How the slope is water.
It depends on yes. 10 meters per 5 meters. It will not be same. Only in the middle river, higher elevation. In the floodplain, lower elevation. Done, huh? Done. So while drawing these cross sections, so these cross sections will give you river shape and length and width. Okay. So when you give the data, water cannot move beyond these lines. Okay. When you are drawing the cross sections, you give in such a way that give in a maximum distance. Okay. That will fix the, for example, the water is going, in a real case, water is going beyond the distance, beyond this line means, so this whatever the analysis, you won't get that line. You will see after the results. So water will be limited within these cross sections only. Okay, when you are drawing cross sections, you draw as much as you want, so that water have flow, like it's have free flow to all the way it go. Okay. Understood what I mean to say? Yes. Water cannot go beyond this thing. Okay? When you are drawing the lines, you draw the big lines. Shall we proceed? Same. Right click, stop editing. Geometry, just save it. Then just go to file, save it. Done? Okay, with this our RAS mapper work is done. Huh? Yeah, save, just stop editing, it will save. Then just go to file and save it. That's it. Just save it. Now automatically model will take this geometry into the geometry file. Okay, just close this. Just close this. Go to edit. Click on geometry data. Here all those cross sections will be visible. For that you need to do one step. Yeah. Click on view. Click on view. Click on this set schematic plot extents. Set schematic plot extents. Click on view. Go to edit. Click on geometry data. Go to view. Click on this set schematic plot extents. Just click on set to computed extents. Click on set to computed extents. Click OK.
Yes.
Okay. If anyone, like, their terrain is also coming up.
Rafi, what is
For
the
anyone?
elevation? What is the number?
You just sit down.
What are the
Yeah, I'll tell. If here terrain is visible, if anyone getting to the terrain,
yes.
you can just go here. You just uncheck this. The terrain is visible means here it is checked. You just uncheck this and only cross sections will be visible. Okay? Here these lines are indicating cross sections. Okay? All these are indicating cross sections. These red dots are indicating back lines. Okay? This is our center line. Again you just set to extend to you. Okay? So this is showing the distance. This 523, 1291, all these are distance from the downstream. Okay? So I told you now, first it will take it the normal depth concept at this, then it will go to this, it will come like this. So it is 523 meter distance from above this. Then it is 1291. Like this indicates the distance. Check in your it should be only one river, only one bridge. That's what distance. Distance from downstream. Last point. It will go from downstream. 0, 500, 1000, 1500. It will go from downstream. Yeah. All of you reach here? Any doubts?
Flooded region. Area of study.
Then just save the geometry. Just go to file and save it. Now here there is option called cross sections, right? Just click on cross section. So this circle is showing, right? This is the pink first cross section. So it is highlighting the cross section view here. So here. Click on cross section. Okay. Understood? So, everyone. So this pink line, it is showing the first cross section line. So this is how this cross section is in the cross section elevations are varying. Okay, we have dem, right? So based on the dem, it is identifying how the elevation are changing in the throat cross section. Okay, so like that you can see here there is option up and down. So next cross section, see it came down. Again next. So this is how the cross section is varying. The cross section elevations are changing like this. Understood? Here you can also see LOB, left bank distance from the center, ROB. So it will calculate the distance. And there is a left bank station, right bank station, and it also gives you contraction, expansion, all those parameters. Here next thing what we do is, along the cross section, we don't have the roughness coefficient value. So we will assume that along the cross section, same roughness. Okay. So usually what will happen? Roughness was less compared to the bank lines, means the flood plains. Compared to flood plains, the roughness was low in the main channel, right? So that water will move freely. So roughness was more in the flood plains. So actually we have to get that data, okay, from authorities. But as of now, we don't know the exact surface roughness value, that Manning's N value. So we are assuming that we'll give you the smooth roughness value at the main channel. Somewhat roughness means more roughness value at the bank lines. And we are assuming that throughout the cross section, that roughness was not varying. So first, what you need to do is, here you can see, delete a cross section. While viewing it,
while we are viewing this cross section, if you find it inappropriate, how to
that you would see everything means regarding geometry. We want to change the line, we want to change the everything. How to do it in the edit geometry? So class mapper. Yes, that's why when you are drawing the cross sections, it should be intersect with the 4 lines, and it should drawn from upstream to downstream. Okay, all these rules you should follow. After fixing everything in the geometry data, then only we come to here. Okay. So what I said, along the cross section, there is no, we are assuming that the roughness is same. So for that, here if you have the data, you can enter like each and every along the cross section at every point what is the roughness is there. But we don't have the data. We are assuming it is a uniform. So what you need to do? Select. This is something one cross section selected, right? So here you just see here first. See here. There is options. Go to options. Here horizontal variation and n values. It is enabled. You disable it. So just click yes. So that line will go here. Okay, that column will be emitted here. So in the same way, change the cross section. Disable it. Like this.
Can you once
Yeah. For example, see, we are assuming that roughness is same throughout the cross section, right? So we need to eliminate this column. Okay. So to do that, go to options. Here it is enabled. That's why that column is highlighted. Disable it. Click yes. Now you see that column is eliminated. So like that you do it for all the cross sections. Here, one by one. Once you cross check, have you done to all the cross sections or not? We are we are not giving that radiation roughness value along the cross section. So we are implementing it. We have, but along the river, we should give. The floodplain also, what is that? So shall I proceed? You can assign that side. Mention just 0.005, like that you can assign. Okay? All of you reach here? So next step is, we have removed this horizontal variation along the cross section, but we have to provide the roughness value in the main channel and the flood plane. Okay? Just save this geometry. And click on tables. Click on tables. And click on Manning's and N value. So here, if you know these are stations, cross sections. This is upstream cross section, this is downstream cross section. So if you know the Manning's value, means roughness value at all the cross sections, you can enter here. This N2 is nothing but main channel. So what is the roughness coefficient value in the main channel at all the cross section? N1 is left bank, N3 is right bank. Yeah. These are cross sections from upstream to downstream. This first one, Manning's N value. Go to tables, Manning's N value. Okay? So that variation is there, you can consider. Yeah. Yes. That, if you know the variation along the channel, if you know the roughness coefficient values at different cross sections, then we can assign those values. But we are assuming that along the river, in the main channel, only one roughness coefficient. So to give the roughness value in the main channel, here just select on that row N2, n equal to 2, just select here and then click on set values. I am assigning one value 0.035. You can give any number, means it should be smooth compared to the floodplain. So in the main channel, I am giving 0.035 and click OK. So now it will assign all the cross sections, the main channel, same roughness. Okay? Click on Click on. So next step. So this is at the main channel. Okay. The left bank in the right bank. Same. Assume that it will be more roughness. So assume 0.06. The right bank also same. 0.06. So all of you reach here. Yeah, I'm telling you now. So in the main channel, it is roughness. See,
N has to be roughness.
ah,
All the values are roughness.
all the three are roughness. N-2 is indicating the main channel.
And the
How
others
this?
are banks.
Yes, the left bank and right bank. They are assigning same roughness throughout the main channel. 0.035. In the banks, left and right bank, we are assigning the same roughness. Understood? Obviously, outside the main channel you have more roughness. So you have just given values like that. Okay? Up to here, clear? So we'll take 10-15 minutes break, then we'll start. Save it. Click OK, and then go to File. Go to File and save it.
I can only charge somewhere over there.
So, till now, what we did, we created the geometry and we have assigned the roughness in the main channel, the right bank and left bank, right? Now, what we need to do now, we have created the geometry and we have assigned the parameters. Now we need to flow the water from upstream to downstream, right? So our flow was unsteady, right? So we have simulated for the event. So it is changing with respect to time. So our flow was unsteady. Let's see both steady and unsteady. First we'll try unsteady. Okay. Now next step is to input our stream flow data at the upstream to the model. Okay. For that is unsteady, right? So go to edit. Click on edit. Click on unsteady flow data. Okay. Click on unsteady flow data. So here, this is the station at the upstream. This is the station at the downstream. So here we need to provide two boundary conditions. Okay. Our upstream boundary condition was our upstream flow. Okay, which was coming from the HMS. But we don't know the water level at the downstream, right? So we are assuming that at the downstream the flow was uniform flow, so it is following the normal depth concept. Okay, so there, to identify the Q, we are giving friction slope value. As it is a uniform flow, the bed slope will be equal to the friction slope. Okay, so area into velocity Q, in that velocity we are giving friction slope. So it is a function of depth. Velocity is a function of depth. We know the Q, so it will calculate the depth. Okay, understood? Our upstream boundary condition is our upstream flow, that is the simulated flow at the outlet of the Netravati basin. Then downstream condition is friction slope. Okay, so first we will give the upstream boundary condition. What will happen in the downstream condition? We don't have the water surface level data, or we don't have the flow hydrograph, a simulated or observed flow hydrograph, or the downstream. So when we fit the model, we are fitting between two stations. So we are having data here, we are not having data here. So if we have the simulated flow hydrograph, you can give that as a downstream boundary condition. So we don't have that downstream flood hydrograph. So what we are assuming? We are assuming that downstream boundary downstream last station is like that is the uniform flow happening. So whatever the depth, which is normal depth concept we are applying, that is nothing but continuity equation. So Q equal to area into velocity. So V equal to 1 by n r to the power of 2 by 3 s to the power of 1 by 2. So there we know Q, we know area means width according to this. So we don't know depth. So y is there? Y is there. Again r to the r means hydraulic radius, area by perimeter. So there also we don't know y. So but and we know the friction slope S. So it will calculate that it will solve that equation. Okay, entire equation. It will throw you one y value. Okay, like that it will go for the upstream. From downstream it will go for the upstream. At the upstream we have the Q value. It will, if that Q is correct, it is matching with that Q, then the whatever the depth you are identifying at the downstream, it is correct. Otherwise, until that it will iterate, it will identify the depth value at each and every cross section. Okay.
My question is, in real time, we have two phases in the upstream, where we fix the upstream condition and downstream. In real time, if we have two basic stations in the one is in upstream, one is at the downstream. If we have the real time data, like say, for example, these many Q-sets, these many Q-sets in upstream and downstream, that can be fixed. That can be given here.
That's what we don't have that downstream water level data. That's why we are going with indirect way. If we have the water surface level data or stream flow data or downstream, you can directly give them. There are multiple options. I'll show you. There are multiple options. So, for example, if you select here, the upstream, just click here. There are three options: stage hydrograph, flow hydrograph, stage or flow hydrograph. Stage hydrograph means water surface levels. At that particular upstream point, if you know the water surface elevations over the event, you can directly give that water surface levels. If we have flow hydrograph, directly we can give flow hydrograph. We have simulated this flow hydrograph, right, using HMS, so you can directly give that. So you just click here. All of you have the output of HMS. If it is there, you take that. If someone's system got shut down right in between, you take the observed data. Take the observed data. Open that Excel sheet. Go to file. Then enter all the data. Rainfall discharge. Yeah. So our third event is from 23rd July. 23rd July to 22nd August. Right? Just select the flow. Sir, which one is 2007 rainfall discharge best flow data. Discharge 2007 discharge. Yeah, overall total inflow. Total. So rainfall discharge. Yeah.
A data, Rafi. AB.
Whoever is having the HMS output, so there you will getting 4 columns, right? The third column was total inflow column, so you can copy that column, or else you open that Excel file. In that observation data is there, observed stream flow data. The third event is from 23rd August, 23rd July, 23rd July to 22nd August. Select that discharge.
Yeah, yeah. No, date
Because this is August 7th. We got some month day. Yes, month day. Yes. The highlight is closed, but you have to bracket that. 23rd July to August 26th.
I told you to say in Excel that the total inflow fund. You use that. You just copy that. That is we have fourth plan. Total inflow. The last term was observed. I'm telling you, whoever don't have that, use that observed. Are you clear? 23rd July to 22nd August. That is the third event we have simulated. August 2007. Just select that. 22nd August. 22nd August. Next month. Just copy. I'll tell you where to paste. Got the data, recharge data? Don't paste it now. Don't paste it, I'll tell you. You need to change the date. Just copy that. All of you got the data where the input is. So before pasting it, okay. Now this window is open, right? So first you need to fix the time interval here, or third event time interval. So for that, you just click on fix start time. Click on fix start time. Here choose the date. 2007, 23rd July. Click OK. Click on fix start time. Open that calendar symbol and choose the date. 23rd July 2007. And here give the time. Yeah, before giving the time, you just interval give 1 day. We have 1 day observation data. Every day 1 day interval. Okay. After that, keep 24 here. 24 hours. Okay. then just click on that column somewhere else. Now our calendar dates was starts with 23rd July 2007. Okay. Now paste here. So, I will show you how to paste. Select all the rows. Select all the rows. Then Control D. Okay. Here we did not mention end date. It will automatically take the dates. Okay. It will automatically throw you the 2 months data. Dates. So in the Excel, copy those, paste it here. Just cross check. Is it like 23rd July value is same and go to 22nd August value are same or not? You just cross check it. Yeah, you are taking from HHM. I am taking upload data. That's why you select all the rows in the column and paste it. While pasting it, select all the rows. All of you reach here. Paste the data. All of it clear? Shall we move to next step? Okay, already copy pasted, right? Yeah. So at the end, if you want to plot, you can plot, you will get a hydrograph. Not required, just click OK. Okay? Next, we need to give the downstream boundary condition. As I told you, we have to give the slope, friction slope. So, the one way to find out the friction slope was, just see here. I'm just first see here, then you will get to know. In the RAS mapper, there is something called measured distance and scale is there. Okay, if you click on that, I'm just showing. For example, if I want to see the distance between these two cross sections or slope between these two cross sections, you can directly start from here and end here. Just double tap it. It will show you the length distance between the two cross sections, and it will also show you the slope. So one way to assign normal depth was, from here you take up to 5 or 10 cross sections, like up to 1 kilometer ahead. How many 1 kilometer, 2 kilometer ahead? How many cross sections are there? Take up to that, then identify the cross section between like all the cross sections. Then take the average slope. Okay, assign that slope as a normal depth. It's at the downstream condition. Okay, understood how to take? So it was an average 0.02. Okay, you just click here, normal depth, click on normal depth. I told you, right, at the downstream, if you have the stage hydrograph, you can view stage hydrograph. If you have the flow hydrograph, you can view. But as of now, we don't have the water surface levels and the flow hydrograph at the downstream. So you are going with the normal depth concept. If you have the rating curves also, you can view the rating curve. Normal depth. So it will ask you to mention the friction slope. Okay. Just mention 0.02. It was the average slope. I just showed how to calculate the slope. Okay, you just enter the value. I just showed how to calculate the slope. That's it. That is how you need to calculate. By mistake, if you have given flow hydrograph and downstream, so you just again you can modify it. Click same, choose normal depth, and give slope at the downstream. Again same way. Upstream station you will select up flow hydrograph.
Two different units, it will calculate.
This is friction. Automatically it will iterate with the alternative equation will come.
Two different conditions.
That is nothing but depth.
ఇప్పుడు ఆ ఉన్న ప్యారామీటర్స్లో ఉన్నాయి తెలుసు లేని ఏదో ఒకటి క్యాలిఫై చేసుకుంటూ మ్యాచ్ చేసుకుంటూ ఉంది ఇచ్చేస్తే మ్యాచ్ చేసుకుంటూ
That is direct depth. It will take direct depth.
yes sir
It is friction. Friction slope. Frictional slope. It's a frictional slope. That's it. Bed slope. They are assuming that is it.
Session is it.
Any doubts? Any clarity missing? What? Okay. Anyway, I will show you. You don't need to do that. But when you are doing for real case, that is the way. You take ahead 10 kilometers or 5 kilometers, identify the slope, then take the average of all those. Then you can assign those values. I'll just show you how to calculate again slope. Okay, go to task mapper. Here the scale is there. For example, I am showing from here to here. Just double click it. It will show you the slope. Again, the same way, calculate slope from here. Again, you calculate it. Like that, we are finding the average slope. Okay, and we are assigning that value at the downstream. Okay. By mistake, if you are given flow hydrograph here, normal depth here, modify it. You can modify it. Okay, till now clear? Up to this done, right? No doubt. So with this, all our input is done. Now we will run. Just save it. Save unstudy flow file. Unstudy flow data, just name it as unstudy. Name it as unstudy and click OK. So here it will be appear. You cannot close this.
Initial condition is not required. As it is on steady.
So initial conditions are not required. If you have, you can do. If the data is there, yeah, if the initial condition values are there, you can do. But it will automatically by default value the data. If we have the information, we can do. So after that, we need to run the study flow. So to run that, just save it once. Click on run. Click on run. Click on unstudy flow analysis. It is like our control panel. Here we need to fix the time interval. Okay. So it has to run. It has to take geometry processor, unstudy flow simulation, post preprocessor, and flood. It has to create the map also, floodplain mapping also. So check all those. And then here you need to give the interval. Our event date is 23rd July, right? 23rd July to 22nd August. So from this calendar, you just select that 23rd July to 22nd August. July 22nd August. Our starting time interval was 24:00. Our ending was 00. And make all the intervals computational settings 1 hour. Sorry, 1 day. After that, just make it all in 1 day. Okay. Then it will, all this information will be stored as plan 01. Okay. Then just click on compute. Click on compute. If any errors come, now it will show. Yeah, all computational settings will be 1 day. Just click on compute. After that, Incomplete. Incomplete. Computation. It's a one will show the if it is showing you are getting error? Yes, sir. Those days are Anyone getting error? Possible for daily, but it can go external. But cross section, it won't go beyond cross section. All of you. All of you clear here? So all done, right? Now we'll see how the flood inundation is happening. Just close this. Close this. Close this. Open RAS mapper. Open RAS mapper. This is the. So just here you can see in the results. Plan 1 is there, right? This is our saved plan. So just click on depth. Just choose the depth. Check that is depth. Okay. So now you can see this is the how the depth is changing throughout the event. Okay. You can see how the depth is changing throughout the event. If you click here maximum, what is the maximum extent of flood? Flood inundation. So, one important observation here. I told you, right? Whatever the cross section we have drawn, water cannot move beyond that. Okay. See here in this case, my cross section is up to here. That's why flood came. It is showed up to here. If I drawn up to here, so flood might happen here also. So while drawing cross sections, how to draw in such a way that you should draw the long parts, long lines, so that it will go all over the wherever the possibility is there. Okay. This is the flood inundation map. You can attach this to satellite map. Just click here, Google satellite. Then you can see the real case. What zone is in critical? Okay. Yeah. Yes. Then after this, if you want to validate this, NRSC people will give you the flood inundation map. So that you can take, and this you can take. These two rasters you can correlate it. You can identify the evaluation performance. Okay. If you want to export this, you can export. In the same way, you can see the velocity, how the velocity is changing, and also you can see the water surface level, how the water surface level is changing. So all I told you, right, all these three are the inputs from the hydraulic model. All of you got this flood inundation map? So if you want to export this as a raster, just click on this plan 1, right click on this plan 1. Here create a new results map layer. Here it will show you the rasters what are all there. You can just click on that. Here you choose the format. Raster only. Yeah, just keep it the same. Then add map. So successfully added. It will be there in the project folder where you have saved project, right? In that the raster map is there. You can add. You can open that raster map in QGIS. Okay. All of it clear? So this is for unstudied flow data, right? Generally, real case is unstudied flow only. Suppose if you want to see, for example, my peak is 15,000 meter cube per second. If I want to see how much area will be in inundation, then you can see that this comes under study flow. So to do that, again you need to create study flow. I'll show you. No. It will mention only maximum. Usually, will take only maximum. If you want particular time series, you have to go to that. Export that. Plan 1 for activity. One by one. Area ground, So this is unstudied flow data. If you want to check for any study flow, means if you want to check for any peak flow, how that flood inundation is happening. So for that, go to edit. That comes under study flow data. Study flow. Here you directly give the flow value. For example, you want to check at 20,000 meter cube per second. Just type that 20,000 and save the study flow data. Just click on file, save it. make it as study. Just I am giving study flow. Click OK. Go to file, save the data. Okay, then close this. Yeah. So, to run for the peak, go to edit, click on study flow data, give the flow here, and then go to file, save it with the name study flow data. Okay, then close it. See here, the study flow it is up here. Okay. Yeah. Okay, all of you reach here. Up to here reach here. Doubt is there, you ask, then only I will come. Go to edit, study flow data, CS that space, enter 20,000. Still it is not coming. This is 24 after 1 2 means hour you have change it to direct. Now see 23, 24, 25. Started from 23, you should end with August 23. Yeah. So now we need to run the study flow. Now we need to run the study flow. It's already all of plain text computed. Which one is missing boundary condition on the screen? Here we forgot to give upstream and downstream condition in the study flow, right? So here you need to mention upstream was what?
Go back and show. Please repeat this one. Please repeat the steps.
Yeah. So what I am telling is, if we have the peak flow, for example 20,000 meter cube per second. Now see at that 20,000 meter cube per second, what is the inundation area? Okay. For that, just go to edit, study flow data. Okay. In this, here we forgot the last time we forgot to mention the boundary conditions. Say the upstream mentioned the 20,000 meter cube per second. Here it will automatically take it from the here 20,000 meter per second. But here you mentioned the downstream normal depth 0.02. Click OK.
Rafi, देखो ऐसे
Reach boundary condition.
okay, right.
Okay. Just click OK. Sir, normal depth. Sir, I put the value
Upstream and
upstream, I think it will take it from here. Here, 20,000 meter per second. Let's see. It is not coming here.
downstream we have to write, huh?
Downstream here.
We have to write.
Normal depth.
We have to write.
Same concept. Right? Just click on normal depth. Here you mention the slope.
Yeah.
It will automatically come here.
0.0.
Yeah. Click OK. Just let's see. Go to run. Study flow analysis. Click on compute. It will run. Okay. So for the same flow, yeah, it is subcritical flow. Why? Because it is a gradually weighted flow. So if the water is not suddenly changing. water was gradually varied. If it is any in between any structure is there, then it will become supercritical. This until that structure will be yeah. So until that it is we are assuming that water generally will flow to the gravity, but it is gradually varied. Flow is gradually varied to supercritical. Now, sediment data we are focusing on sediment. I need some information related to sediment. We are not given. Yeah, we will also get sediment. Yeah. Now we can see there are so many options in across. We have seen just 1% of it. So many other options are there. You can explore it. There is a manual is there in the across website. It is not only used for flood inundation, it will also use it for sediment, so many other purposes. Okay, this is one way to get the inundation map. Okay. Now let's see with this 20,000 meter cube per second how the flood inundation map is changing. Click on RAS mapper. Okay, in the plan 2, see now it got extended, right? It was more compared to the previous. Yeah, it is not changing with respect to time, it won't change. Yeah, you can see. There is option called 3D. If you want to see, you can click OK. You can also see in 3D. I think some systems will support, some systems not support. It is just a 3D view. How the cross section is there, how the water is flowing, all those visuals visible. That option. Yeah. It's okay. Okay, it is done. So with this across is completed. You practice it one more time. Today, tonight, if you have any doubts, I'll be here. You can ask me. Okay? If the 20,000 meter cube per second is constantly explores throughout the cell, because there is study for it, it's not changing with respect to time. Because it is only one foot. Same on ఇండిపెండేషన్ వస్తుంది స్నాప్ చూసారు కదా స్నాప్ ఇందులో సేమ్ ఈ ఎక్స్ప్లోర్ లేయర్స్ పెట్టి ఆ లేయర్ నుంచి ఏరియా కనుక్కోవాలి అటు కంటే So all of you reach up to here, right? Okay, we close it.